If everything began from one point, where is the center now? What if the universe is expanding, but from nowhere? Can something grow without having a middle? If we're not in the center, who is? The universe has no edges. But what about the center? To find the center of the universe, you'll have to unlearn everything you thought you knew. Let's begin. Have you ever wondered about your place in the vast cosmos? We humans like to imagine that everything begins somewhere, that every story has a center, a starting point, a place to return to. But in the cosmos, this comforting idea gently unravels. The universe is expanding, yet not from any single place. Every galaxy moves away from every other, as if space itself is stretching. There is no edge, no middle, just an endless fabric, growing quietly in all directions. Tonight, we explore a truth that feels strange at first, but brings a unique comfort in the end. The universe has no center, and you are not far from it. As you drift into sleep, imagine yourself floating through this boundless space, part of something so much greater than yourself, yet perfectly at home in it. The stars above you are not arranged around any central point. They simply exist, scattered across the endless night. And you, listening to these words, are a part of this magnificent arrangement, this cosmic dance that has no lead, no focal point, only participants. From the ground beneath our feet, we see the sun rise and fall in its daily journey. We watch stars move across the night sky in their eternal procession. To ancient observers across every civilization, this created a powerful and persistent illusion that we were at the center of everything. The sky appeared to revolve around us, and for thousands of years, this geocentric model seemed perfectly reasonable. The heavens circled Earth, and we stood at the still point around which all celestial bodies danced. This perspective was not just convenient, it was comforting. It placed humanity at the cosmic center, giving us purpose and meaning through position. The Greek astronomer Ptolemy formalized this view in the 2nd century, creating a mathematical model where planets moved in complex patterns around Earth. For over 1,000 years, this remained our understanding. We were central, we were important. The universe acknowledged this by placing us at its heart. But as our tools improved and our observations became more precise, cracks began to appear in this comforting narrative. The movements of planets didn't quite match the predictions. The elegant simplicity that should accompany truth was missing, and brave thinkers began to question whether our centrality was fact or simply a perspective bias. As our understanding grew, we replaced Earth with the Sun at the center of our cosmic model. Copernicus proposed this heliocentric view, and though it took generations to accept, eventually the evidence became overwhelming. Earth was just one planet among several, orbiting an ordinary star. We had taken our first step away from the center, but this was just the beginning of our cosmic demotion. Later, as telescopes revealed the true nature of stars, we realized our solar system is just one of billions in the Milky Way galaxy. The Sun, once the center of everything, was revealed to be an ordinary star located nowhere special in a spiral arm, some 26,000 light-years from the galactic center. Then, in the early 20th century, we learned our galaxy is one of billions more. Edwin Hubble showed that many of the fuzzy patches in our telescopes were not gas clouds within the Milky Way, but entire galaxies far beyond our own. The universe expanded exponentially in our understanding, and with each expansion, we became less central, more peripheral. The deeper we looked into space, the less special our position seemed, but still, the human instinct remains. We want to believe there is a true center, a cosmic origin, a point from which everything expanded. Surely, we think, if we trace the paths of all galaxies backward, they must converge at a single point. The Big Bang must have happened somewhere, and that somewhere must be the center of everything. But this intuitive assumption, like so many before it, does not match how the universe actually works. The expansion of the universe doesn't require a center. It doesn't emanate from a point. Like the surface of an inflating balloon, every point moves away from every other, with no preferred place. If you draw dots on a balloon and then inflate it, each dot sees all others moving away. None of them is the center of the expansion. The the surface itself is stretching. This analogy helps us understand cosmic expansion, though it has limitations we'll explore later. The critical insight is that the universe isn't expanding into something else. It's not like an explosion sending debris into empty space. Instead, it's expanding as something. Space itself stretches, carrying galaxies along with it. And in that truth, the idea of a center simply dissolves. There is no central point from which everything recedes. Every galaxy observes all others moving away. If observers on a distant galaxy looked at our Milky Way, they would see it moving away from them. They would see all galaxies receding. From their perspective, they might appear to be at the center, just as we might think we are from our vantage point. But neither perspective is privileged. Neither is correct or incorrect. They are simply different viewpoints in a universe where position is relative. This realization challenges our deep human need for special placement. Throughout history, we have consistently placed ourselves at the center of our models of reality. We were the center of the Earth. Then Earth was the center of the solar system. Then the solar system was near the center of the galaxy. With each discovery, we have had to move our understanding of centrality, until finally, we must abandon it altogether. The psychological impact of this decentering cannot be overstated. It represents not just a shift in astronomical understanding, but a profound change in how we conceive of our place in existence. We are not special by position. We are not central by location. The universe does not revolve around us, literally or figuratively. But in this apparent demotion lies a beautiful truth. If there is no center, then no place is privileged over any other. Every location in the cosmos is equally valid, equally part of the whole. Our position may not be special, but neither is it diminished. In a universe without a center, every point can be seen as central to its own perspective. This is more than an astronomical fact. It's a philosophical reframing. The lack of cosmic centrality invites us to find meaning not in position, but in existence itself. Not in being at the center, but in being at all. There is a profound democracy in a centerless universe. No location is elevated above others. No position confers special status. Some resist this view, seeking to preserve human distinctiveness through other means. If we are not central in space, perhaps we are central in purpose. Perhaps the entire universe was designed with us in mind, even if we do not occupy a geometrically central location. But modern cosmology suggests even this view is questionable. The vastness of space, the billions of galaxies, each with billions of stars, and likely billions of planets, makes human centrality in any sense difficult to maintain. As we lie here contemplating the night sky, we must come to terms with this strange truth. The universe expanded from an initial state of incredible density and heat, but this expansion did not have a center. It happened everywhere at once. Every point in today's universe was present at the beginning, compressed together with all other points. There was no outside, no empty space into which the universe expanded. There was only the universe itself, stretching and cooling. This concept challenges the limits of our imagination. We are accustomed to thinking of explosions and expansions as having origins, centers from which they propagate. But cosmic expansion defies this familiar pattern. It is not an explosion in space. It is an expansion of space itself, and such an expansion requires no center. The mathematics of general relativity, which describes the behavior of space, time, and gravity, confirms this understanding. In the equations that model cosmic expansion, no point is treated differently from any other. The formulas work the same way regardless of which location you consider. This mathematical symmetry reflects the physical reality of a universe without a preferred center. As we enter deeper sleep, let us release the need to place ourselves at the center of everything. Let us find comfort in being part of a vast, expanding cosmos, where our location may not be special, but our existence, our consciousness, our ability to contemplate these very questions remains remarkable. The universe may not revolve around us, but we are still integral to its unfolding story. In the chapters that follow, we will explore more deeply how space expands, what the Big Bang really was, and how we can visualize a universe without a center. We will see how observations from any galaxy would show the same pattern of expansion, and how the oldest light in the universe confirms the symmetry of space. We will consider the limits of our observable universe and what lies beyond, and contemplate the philosophical implications of living in a cosmos without a center. But for now, let this first truth settle in your mind as you drift further into rest. The center you've been seeking does not exist, and yet you are not lost. You are exactly where you should be, floating in a sea of stars that spreads in all directions, with no shore more important than any other. In this vast ocean of night, your position is not central, but it is perfect. It is yours. To understand why the universe has no center, we need to grasp what cosmic expansion truly means. It's not merely that galaxies are flying away through space like debris from an explosion. The reality is far more profound. Space itself is stretching, expanding, like a fabric being pulled in all directions simultaneously. This concept challenges our everyday intuition but holds the key to understanding our centerless cosmos. Imagine you're looking at a grid drawn on a rubber sheet. If you stretch the sheet, the grid lines move apart. The distance between any 2 points increases, not because the points are moving across the surface, but because the surface itself is expanding. This is precisely what happens in our universe, but in 3 dimensions rather than 2. The fabric of space stretches, carrying galaxies along with it. This change in scale affects everything over great cosmic distances. The farther 2 objects are from each other, the faster they appear to move apart. This relationship, known as Hubble's law, is exactly what we would expect if space itself is expanding uniformly. The speed of recession is proportional to distance, a pattern that would be observed from any galaxy in the universe. A helpful analogy is to picture raisins embedded in a loaf of rising bread dough. As the dough expands during baking, every raisin moves away from every other raisin. A raisin on one edge sees all other raisins moving away. A raisin in the middle also sees all other raisins moving away. None sits at the center of the expansion. None is the origin from which all others flee. The motion is a result of the expanding medium, the dough, carrying the raisins along with it. This is precisely how cosmic expansion works. The Big Bang did not explode into empty, pre-existing space. It wasn't like a firecracker detonating in a room. Instead, it created space and time. And that creation continues as space expands. Every galaxy observes all others receding, not because any particular galaxy is central, but because the space between them is growing. The mathematics of general relativity describes this expansion precisely. In Einstein's field equations, space itself is dynamic. It can stretch, contract, and bend. The solutions to these equations that match our observations show a universe expanding equally in all directions, with no preferred center. This mathematical symmetry reflects a physical reality. Expansion happens everywhere at once. When we observe distant galaxies, we find they are moving away from us in all directions. The farther the galaxy, the faster it recedes. This observation led some to initially believe that we must be at the center of the expansion. After all, if everything is moving away from us, aren't we special? But this conclusion misses a crucial point. Observers in those distant galaxies would see exactly the same pattern. From their perspective, all galaxies, including our Milky Way, would be moving away from them. They, too, would appear to be at the center. This remarkable symmetry, that every observer sees the same pattern of expansion, is possible only if space itself is expanding. It cannot be explained by galaxies simply moving through static space. In that scenario, there would indeed need to be a center, but in an expanding space, no center is required or even possible. It's important to note that not everything in the universe is being carried apart by expansion. Locally, gravity binds objects together. Our solar system isn't expanding. The Earth isn't getting larger. The Milky Way galaxy holds together through gravitational attraction. Even clusters of galaxies remain bound by their mutual gravity. But on the largest scales, beyond clusters and superclusters, expansion dominates. The fabric of space stretches, and distant galaxies recede from one another. The rate of this expansion has changed over time. In the earliest moments after the Big Bang, expansion was incredibly rapid. It then slowed as the gravitational attraction of matter worked against the expansion. But approximately 5 billion years ago, something unexpected happened. The expansion began to accelerate. Astronomers attribute this acceleration to a mysterious force called dark energy, which seems to be intrinsic to space itself. The more space expands, the more dark energy there is, and the faster the expansion becomes. This acceleration adds another layer to our understanding of cosmic expansion. Not only is space stretching, but the rate of stretching is increasing. Yet even with this acceleration, there is still no center. Dark energy appears to be uniformly distributed throughout space, affecting the expansion rate equally in all regions. The expansion of space has profound implications for our observations of the distant universe. Light traveling through expanding space gets stretched, shifting to longer wavelengths. This phenomenon, called redshift, is how we measure the expansion rate. The light from distant galaxies shows a redshift proportional to their distance from us, exactly what we would expect in a uniformly expanding universe. This redshift also means that the farther we look into space, the farther back in time we see. Light from a galaxy, 10 billion light-years away, has been traveling for 10 billion years to reach us. We see that galaxy not as it is now, but as it was when the universe was much younger. This gives us a window into cosmic history, allowing us to trace the evolution of the universe back toward its beginning. As we look at more and more distant galaxies, we see space expanding faster and faster in the past. If we could trace this expansion back to its origin, we would find all points in today's universe compressed into an incredibly hot, dense state. This initial state is what we call the Big Bang. But critically, the Big Bang happened everywhere at once. It wasn't a point in pre-existing space, it was the beginning of space itself. Understanding that the Big Bang occurred everywhere simultaneously is key to grasping why the universe has no center. There was no single point from which everything expanded. Every location in today's universe was present at the beginning, compressed together with all other locations. As space expanded, these points moved apart, but none can claim to be the original center. This concept is difficult to visualize because our minds are accustomed to thinking of explosions and expansions as having origins, central points from which they spread. But cosmic expansion follows a different pattern. It is not centralized but uniform throughout space. Some people wonder if there might be a center of mass of the universe, a point around which all matter is evenly distributed. But current observations suggest the universe is homogeneous and isotropic on the largest scales. This means matter is distributed uniformly when averaged over sufficiently large volumes. There is no special point that could be identified as a center of mass. Others ask about the edge of the universe. If there's no center, is there at least a boundary? Current evidence suggests there is not. The universe could be infinite in extent, or it could be finite but unbounded, like the surface of a sphere, which has finite area but no edge. In either case, there would be no center and no boundary. Consider a two-dimensional analogy, the surface of the Earth. If you're an ant walking on this surface, you can go in any direction without ever reaching an edge. The surface is finite in area, but has no boundary. It also has no center on the surface itself. The center of the Earth lies below the surface, in a dimension the ant cannot access. Our three-dimensional space could be similar, curving in a higher dimension we cannot directly perceive. As you drift deeper into sleep, imagine the fabric of space gently stretching in all directions. Galaxies move apart like points on an inflating balloon. None is central, none is special by position. Yet each contains its own wonders, stars, planets, perhaps life. In this expanding cosmic tapestry, your location may not be central, but it is unique. It is the vantage point from which you observe the universe. And that perspective, that consciousness, that capacity for wonder is extraordinary, regardless of where it exists in the cosmic expanse. In the next chapter, we'll explore one of the most common misconceptions about the universe, that the Big Bang was an explosion from a point. We'll see how this misconception contributes to the mistaken belief that the universe must have a center. We'll discover that the beginning of the universe was not an event at a location, but an event that created location itself. But for now, rest in the knowledge that the fabric of space stretches all around you, a vast cosmic sea with no shore more significant than any other. In this boundless ocean, you float, not at the center, but exactly where you belong. As the night grows deeper and your thoughts drift with the expanding universe, remember that every point in space experiences this same gentle stretching. The galaxies don't know they're moving apart. They simply exist in a space that grows. And you, lying here contemplating these cosmic truths, are part of this grand expansion. Your atoms were forged in ancient stars. Your body exists in space that has been expanding for nearly 14 billion years. You are not at the center of it all, but you are made of the same stuff as the stars, participating in the same cosmic dance of matter and energy, space and time. The phrase Big Bang has become firmly embedded in our cultural vocabulary. We hear it in science documentaries, read about it in books, and see artistic representations of it in museums and media. But this familiar term carries within it a fundamental misconception that leads many to misunderstand the nature of our universe's beginning. The Big Bang sounds like a blaster loud, violent eruption from a single point in space. This mental image suggests an explosion that sent matter flying outward from a central location, much like a firework or a detonated bomb. But in reality, the Big Bang wasn't an explosion in space. It wasn't an event that happened at a particular location within a pre-existing void. It was the rapid expansion of space itself, the very birth of distance, dimension, and locality. This distinction is crucial for understanding why the universe has no center. When we imagine an explosion, we picture it occurring somewhere. A bomb detonates in a building. A star goes supernova in a galaxy. These events have specific locations, places you could point to and say, it happened there. But the Big Bang doesn't fit this pattern. It didn't happen somewhere within something larger. Everywhere was the Big Bang. Not just here, not just over there, everywhere simultaneously. The universe didn't begin as an infinitesimally small point surrounded by empty space, which then exploded outward. Instead, it began as a static, incredibly hot, dense, and uniform condition that encompassed all that existed. There was no outside to the early universe. There was no empty space into which it expanded. The entirety of what would become our cosmos was compressed into this initial state. From that early moment, space has been stretching, carrying matter and energy with it. But this stretching wasn't radiating outward from a central point. It was happening everywhere at once, with every region of space expanding away from every other region. This is why there is no center to the universe. The beginning happened uniformly across all of existence. Time itself began in that moment, so there is no before the Big Bang. And space began in that moment, so there is no outside location where the Big Bang occurred. Asking where the Big Bang took place is similar to asking what's north of the North Pole. The question assumes a frame of reference that doesn't exist. At the North Pole, every direction is south. There is no north to travel toward. Similarly, there is no location where the Big Bang happened, as distinct from other locations. It happened everywhere at once. The term Big Bang was actually coined somewhat mockingly by astronomer Fred Hoyle, who preferred an alternative theory called the steady-state model. Hoyle intended the name to make the idea sound absurder, Big Bang, out of nothing. But the evidence for this model became overwhelming, and the catchy name stuck, despite its misleading connotations. A more accurate but less dramatic name might be the rapid expansion or the cosmic beginning. These terms better capture the nature of the event without implying an explosion from a point. But Big Bang remains firmly established in both scientific and popular discourse, so we continue to use it while being careful to clarify its true meaning. Evidence for the Big Bang model comes from several observations. First, we observe that the universe is expanding, with distant galaxies moving away from us at speeds proportional to their distance. Second, we detect the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. Third, we measure the abundance of light elements like hydrogen, helium, and lithium, which match predictions of what would have been produced in the first few minutes after the Big Bang. These observations support a model where the universe began in an extremely hot, dense state and has been expanding and cooling ever since. But none of these observations indicates a central point from which everything expanded. Instead, they show a universe that is remarkably uniform on the largest scales, consistent with an expansion that happened everywhere at once. In the earliest moments after the Big Bang, or perhaps we should say, during the Big Bang, since the event itself encompasses the initial expansion, the universe was filled with an incredibly hot plasma of elementary particles. As space expanded and cooled, these particles combined to form protons and neutrons, then atomic nuclei, and eventually complete atoms. The first stars and galaxies formed from clouds of hydrogen and helium gas that collapsed under their own gravity. Throughout this process of cosmic evolution, there was never a central point from which everything emerged. Every region of space has a similar history, cooling and evolving as the universe expanded. The large-scale structure we observe today, the cosmic web of galaxy clusters and superclusters, emerged from tiny fluctuations in the density of the early universe, not from an explosion radiating from a center. Understanding the Big Bang as the beginning of space and time, rather than an explosion within space, helps resolve several paradoxes. For example, people sometimes ask, what is the universe expanding into? If the Big Bang were an explosion, this would be a reasonable question. But since space itself is expanding, there is no outside for it to expand into. The universe isn't getting larger within something else. It's simply that the distances between objects within the universe are increasing. Similarly, people often ask, what caused the Big Bang, or what came before the Big Bang? These questions assume that the Big Bang occurred within an existing framework of space and time. But if the Big Bang created space and time, then the concepts of before and cause become problematic. Causes precede their effects in time, but if time itself began with the Big Bang, then there is no before in which a cause could operate. These are profound questions that push at the boundaries of our understanding, where physics meets philosophy. Some theoretical models propose multiverses or cyclic universes that might provide context for our Big Bang. Others suggest that quantum effects near the beginning might blur the very concept of a distinct starting point. But all mainstream models agree that from the perspective of our universe, the Big Bang represents the limit of what we can know through observation. The fact that the universe began everywhere at once has profound implications for our place in the cosmos. There is no special location that can claim to be the site of the beginning. No galaxy, no star system, no planet can be said to occupy the position where it all started. The beginning belongs equally to all places. This universality of origin creates a kind of cosmic democracy. No position in space is privileged by being closer to the starting point. Each location can trace its history back to that same initial state of hot, dense matter and energy. Your atoms, the atoms making up the Earth, the atoms in the most distant galaxy Sol, were present in that early universe. All have experienced the same cosmic expansion and evolution. As you lie here contemplating these ideas, consider that the space around you, the very dimensions in which you exist, emerged from that initial rapid expansion. The Big Bang isn't something that happened far away and long ago. Its effects surround you. You exist within the continuing aftermath of that initial expansion. The cosmic microwave background radiation, the afterglow of the Big Bang, passes through your body at this very moment. The early universe was remarkably uniform, but not perfectly so. Tiny quantum fluctuations in the density of matter and energy were stretched by cosmic expansion, eventually growing into the structures we see today: galaxies, clusters, and the cosmic web. Without these slight imperfections in the early universe, stars and galaxies would never have formed. The cosmos would be a featureless fog of hydrogen and helium, gradually cooling for eternity. But those small variations in density allowed gravity to draw matter together, forming the first stars perhaps 100 million years after the Big Bang. These massive, short-lived stars forged heavier elements in their cores and scattered them through space when they exploded as supernovae. Later generations of stars formed from gas enriched with these elements. Eventually, planets coalesced around some of these stars, and on at least one such planet, life emerged, evolved, and developed intelligence capable of pondering its own origins. This cosmic history is shared by all parts of the universe. It isn't centered on any particular location. It's a story that belongs to every galaxy, every star system, every planet. The details vary. Some regions formed galaxies earlier than others. Some have higher concentrations of stars. Some may harbor life, while others don't. But the broad narrative is universal. When we observe distant galaxies, we're looking back in time because of the finite speed of light. A galaxy 10 billion light-years away appears to us as it was 10 billion years ago. This gives us a window into the past, allowing us to see earlier chapters of cosmic evolution. Yet even these ancient galaxies weren't at the center of the Big Bang. They too emerged from that same initial expansion that created all of space. As our understanding of cosmology has evolved, we've had to abandon many intuitive ideas about the universe. The notion of an explosion from a central point is one of these. It's a natural way for humans to think about beginnings, but it doesn't match the reality revealed by observation and theory. The Big Bang happened everywhere. The beginning occurred at every point in space simultaneously. There is no center from which everything emerged. This realization can be disorienting. Our minds seek specific locations for events. We want to point and say, it started there, but the universe challenges us to think differently. It asks us to conceive of a beginning that has no special location, an expansion that proceeds from everywhere at once. As you drift deeper into sleep, let this cosmic perspective settle in your mind. You don't need to be at the center of the universe to be part of its story. Your atoms were present in that initial hot, dense state. They've experienced the entire nearly 14 billion year history of cosmic expansion and evolution. Through you, the universe has developed consciousness and the ability to contemplate its own origins. In that sense, you are not peripheral to the cosmic story. You are central to one of its most remarkable developments, the emergence of mind from matter, of awareness from the mindless interactions of particles and forces. In the next chapter, we'll explore a common analogy used to visualize the expanding universe, the inflating balloon. We'll see how this analogy helps us understand a universe without a center, but also where the analogy breaks down. We'll discover that while visual models can aid our understanding, they also have limitations when representing the true nature of cosmic expansion. But for now, rest in the knowledge that the Big Bang wasn't a distant event in space. It was the beginning of space itself, occurring everywhere at once, including the very spot where you now lie, contemplating the cosmos. A common way to visualize the expanding universe is with the analogy of an inflating balloon. This simple model helps us grasp certain aspects of cosmic expansion, but like all analogies, it has its limitations. Let's explore this visualization and understand both what it reveals and where it falls short in representing our centerless cosmos. Imagine you have a dark rubber balloon. Using a marker, you draw small dots all over its surface. These dots represent galaxies in our universe. Now, as you begin to inflate the balloon, something interesting happens. Each dot moves away from every other dot. If you were an infinitesimally small observer living on one of these dots, you would see all other dots receding from you in all directions. This is the key insight the balloon analogy provides. Every dot sees the others moving away. Every dot appears to be at the center of the expansion. None actually is. The expansion happens because the surface itself, the two-dimensional skin of the balloon, is stretching. The dots aren't moving across the surface. They're being carried along as the surface expands. This perfectly mirrors what happens in our universe. Galaxies see all other galaxies moving away from them. Each could claim to be at the center of the expansion, but this is merely a perspective effect. The expansion occurs because space itself stretches, carrying galaxies along with it. In the balloon analogy, the distance between any two dots increases as the balloon inflates. Moreover, dots that are farther apart move away from each other faster than dots that are close together. This mirrors Hubble's law in our universe, the observation that distant galaxies recede more rapidly than nearby ones, with velocity proportional to distance. Another insight from the balloon model is that there is no center on the surface. The center of the balloon exists, but it's in the interior region the two-dimensional surface dwellers cannot access. For them, living on the surface, every point is equal. None is closer to the edge, there is no edge on the surface, and none is at the center. The center isn't on the surface. In this analogy, our universe is the surface C0, the inside volume of the balloon. The universe doesn't expand into space, it simply expands. We are like the hypothetical beings confined to the balloon's surface, experiencing a universe that has no center within our dimensional framework. But here's where the analogy begins to show its limitations. The balloon is a two-dimensional surface, existing in three-dimensional space. Its center lies outside the universe of the surface, in a higher dimension. Our actual universe is three-dimensional, or rather, three spatial dimensions plus time, and we don't know if there's a higher dimensional outside in which it's embedded. While mathematics can describe higher dimensions, and some theoretical physics models propose extra dimensions beyond the three spatial dimensions we experience, we have no observational evidence for such dimensions, at least not on macro scales. So while the balloon helps us visualize expansion without a center, it also leads us to imagine something beyond a higher dimensional space, containing our universe that may not exist. Another limitation is that the balloon has a clear boundary. Its surface is finite in area, with a definite size at any moment. Our universe might be infinite in extent, or it might be finite but unbounded, like the surface of a sphere, but in 3 dimensions. Current observations can't tell us which is the case, as we can only see the observable universe, the portion from which light has had time to reach us since the Big Bang. The balloon analogy also doesn't capture the fact that gravity works against expansion on smaller scales. In our universe, galaxy clusters and smaller structures stay bound together by gravitational attraction, even as the space between clusters expands. On the balloon, all dots move apart, regardless of scale. To make the analogy more accurate, we would need to imagine some dots glued together in clusters that maintain their internal structure while the clusters themselves move apart. Additionally, the balloon expands into existing space around it. Our universe doesn't expand into anything. Space itself expands, creating more distance between objects without requiring any pre-existing void to expand into. The balloon needs room around it to grow. The universe creates its own room by expanding. The balloon analogy also suggests that the expansion is driven by some external force, the person blowing into the balloon. In reality, the expansion of the universe is an intrinsic property described by Einstein's equations of general relativity. In the current era, this expansion is accelerating due to a mysterious force called dark energy, which appears to be inherent to space itself. The more space expands, the more dark energy there is, driving even faster expansion in a sort of cosmic feedback loop. Despite these limitations, the balloon analogy remains one of the most helpful visualizations for understanding a universe without a center. It directly challenges our intuition that expansion must proceed from a central point, showing instead how it can occur uniformly across an entire surface. Sometimes, physics teachers extend the balloon analogy by placing small coins on the balloon's surface to represent galaxy clusters. As the balloon inflates, the distance between coins increases, but the coins themselves don't grow larger. This helps illustrate how expansion affects large-scale structures while leaving smaller, gravitationally bound objects intact. Other visualizations include a rising raisin bread, where the dough represents expanding space and the raisins represent galaxies. As the bread bakes and rises, all raisins move away from each other, with no raisin at the center of the expansion. This analogy has the advantage of being 3-dimensional, but still doesn't capture all aspects of cosmic expansion. Computer simulations provide perhaps the most accurate visualizations of cosmic expansion. These models start with conditions matching the early universe and apply the laws of physics to show how structures form over time. When viewing these simulations, one can see that expansion occurs everywhere at once, with no preferred central point. As you contemplate these visualizations, it's worth considering what they tell us about our conceptual limitations. We struggle to picture a 3-dimensional space that expands without having a center and without expanding into anything. Our minds, evolved to understand the middle-scale world of terrestrial objects, strain at the frontiers of cosmological thinking. Yet mathematics allows us to describe what we cannot easily visualize. The equations of general relativity provide a precise mathematical description of an expanding universe without a center. In these equations, expansion is a property of space itself, requiring no central point and no external void to expand into. Albert Einstein initially believed the universe must be static, neither expanding nor contracting. When his equations suggested an expanding universe, he introduced a cosmological constant to counteract expansion and maintain a static cosmos. Years later, when Edwin Hubble's observations confirmed that the universe is indeed expanding, Einstein called this adjustment his greatest blunder. Ironically, modern observations of accelerating expansion have revived the concept of a cosmological constant, now interpreted as dark energy. The discovery that the universe is expanding fundamentally changed our understanding of cosmic history and destiny. It led directly to the Big Bang Theory, the realization that if the universe is expanding now, then in the past it must have been smaller, denser, and hotter. Tracing this expansion backward in time leads inevitably to an initial state of incredible density and temperature, the beginning we call the Big Bang. Looking forward, the accelerating expansion suggests a future where galaxies beyond our local group will eventually recede so rapidly that their light can no longer reach us. In the far distant future, observers in the Milky Way, by then merged with the Andromeda Galaxy, would see a nearly empty universe, with all other galaxies having disappeared beyond an expanding horizon. As you drift deeper into sleep, imagine yourself floating above the surface of an expanding balloon. You see the dots moving apart, each dot experiencing the same phenomenon, others receding. Now, try to shift your perspective. Imagine a three-dimensional grid expanding uniformly in all directions, carrying galaxies along with it. There is no center to this expansion, no edge, just space itself stretching everywhere at once. In this mental model, you float not on the outside looking in, but within the very fabric of expanding space. You are part of this cosmic stretching. Your atoms maintain their integrity through electromagnetic forces. Your body holds together. Your planet orbits its star undisturbed. But the vast gulfs between galaxy clusters widen imperceptibly with each passing moment. This is your universe, not bounded like a balloon, not expanding into emptiness, not emanating from a central point. It is a cosmos where space itself grows, carrying the light of distant stars across ever-increasing distances. A universe that had no center at its beginning and has no center now. A reality more subtle and more fascinating than our everyday intuitions can easily grasp. In the next chapter, we'll explore another key insight, that observers anywhere in the universe would see the same pattern of expansion that we do. We'll discover how this universal perspective confirms the absence of a cosmic center and reinforces the cosmological principle, the idea that the universe looks roughly the same from any vantage point on the largest scales. But for now, let the image of the expanding balloon rest lightly in your mind, a simplified but helpful model of a universe where every point expands away from every other, with no point claiming the privileged status of being the center. One of the most powerful insights of modern cosmology is both simple and profound. Every observer in the universe, regardless of their location, would see galaxies moving away in all directions. This universal perspective is not a coincidence but a fundamental property of cosmic expansion that definitively shows why the universe cannot have a center. If you were to travel to a distant galaxy, millions or billions of light years from the Milky Way, and set up your telescopes, what would you see? You would observe galaxies receding from you in all directions. You would measure their velocities and find they follow Hubble's law: farther away a galaxy, the faster it moves away from you. From your new vantage point, it would appear as though this distant galaxy is at the center of an expanding universe. But this is precisely what we observe from Earth. Looking out from our Milky Way, we see galaxies retreating in all directions, with speeds proportional to their distances. This creates the illusion that we are at a special location, the center from which everything is moving away. But we know this cannot be true for both locations simultaneously. We cannot be at the center, and observers in a distant galaxy also be at the center. The resolution to this apparent paradox lies in understanding that neither location is truly central. The appearance of being at the center is a perspective effect that would be experienced by observers anywhere in the universe. This universality of viewpoint is possible only if space itself is expanding, rather than galaxies simply moving through static space. This uniformity is built into the very structure of space. Cosmologists describe the universe as isotropic and homogeneous on the largest scales. Isotropic means it looks the same in all directions from a given point. Homogeneous means it looks the same at every point. Together, these properties form what we call the cosmological principle, the fundamental assumption that the universe has no special places or directions when viewed at sufficiently large scales. The evidence for isotropy comes from our observations of the distant universe. When we look in different directions, we see roughly the same distribution of galaxies. There is no preferred axis, no special direction that contains noticeably more or fewer galaxies than others. The large-scale structure of the universe resembles a sponge or foam, with filaments and clusters of galaxies separated by vast voids. But this pattern appears similar in all directions. The evidence for homogeneity comes from comparing our observations with those that would be made from other galaxies. While we cannot physically travel to distant galaxies to make measurements, we can predict what observers there would see based on our understanding of physics and the distribution of matter. These predictions consistently show that other observers would witness the same large-scale patterns we do. Perhaps the strongest evidence for the cosmological principle comes from the cosmic microwave background radiation, the oldest light in the universe. This radiation, released about 380 years after the Big Bang, when the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms, has been traveling through space ever since. When we map this background radiation across the entire sky, we find it is remarkably uniform. After accounting for our own motion through space, which creates a slight Doppler shift in the radiation, the temperature of this background light varies by only about 1 part in 100, 0 across the entire celestial sphere. This extraordinary uniformity testifies to the isotropy of the early universe. The tiny temperature fluctuations that do exist in the cosmic microwave background are themselves isotropically distributed. There is no preferred direction to these variations. They represent the seeds of cosmic structure, the slightly denser regions that would eventually grow into the galaxies and clusters we see today. Their uniform distribution across the sky confirms that the universe has no special axis or center. If the universe did have a center from which expansion proceeded, we would expect to see systematic differences in the cosmic microwave background, depending on which direction we looked. Regions closer to this hypothetical center would have different properties than regions farther away. We observe no such differences, confirming that expansion happens uniformly throughout space. The laws of physics themselves appear to be the same throughout the observable universe. When we analyze the light from distant galaxies, we find the same spectral patterns produced by the same atomic and molecular processes that occur in our laboratories on Earth. The fundamental constants that govern these processes, the speed of light, Planck's constant, the gravitational constant, and others show no variation with location or direction, as far as we can measure. This universality of physical law reinforces the principle that no location in the universe is special. The cosmos plays by the same rules everywhere. There is no favored region where different physics applies, no central hub from which the laws of nature emanate. Every galaxy is at the center of its own observable universe, not because it's truly central, but because light has only had time to travel so far since the Big Bang. The observable universe is the spherical region around any observer from which light has had sufficient time to reach them. For us on Earth, this sphere extends about 46.5 billion light-years in radius, larger than the 13.8 billion years age of the universe, because space itself has expanded during the light's journey. If you were in a galaxy 10 billion light-years from the Milky Way, you would have your own observable universe, a sphere centered on your galaxy, with some regions overlapping our observable universe, and some regions beyond what we can see. Your cosmic horizon would include galaxies invisible to us, just as our horizon includes galaxies invisible to you. This relativity of perspective is a natural consequence of the finite speed of light combined with cosmic expansion. It means that every observer has their own unique window on the universe, their own sphere of visibility centered on their location. This creates the illusion of centrality for every observer, but it's just the Tarn illusion. The center you perceive is simply your vantage point, and everyone else has one too. In this sense, the universe has infinitely many centers of observation, but no true geometric center. Each observer is at the center of what they can see, but not at the center of the universe as a whole. This concept challenges our intuitive notion of what it means to be at the center of something. We typically think of a center as a special place, like the center of a city or the center of a circle. But in an expanding universe governed by the cosmological principle, every place is on equal footing. None is geometrically special. Consider an infinite chessboard with identical pieces distributed uniformly across it. Every square would look the same as every other. None could claim to be the center of the board. This is similar to our universe on the largest scale, a uniform distribution of galaxies and clusters in which no region is distinctive enough to be considered central. Of course, on smaller scales, the universe is far from uniform. There are rich clusters of galaxies and vast empty voids. Some regions contain quasars or massive black holes or intense star formation, while others are relatively quiet. But these variations are like local weather patterns on Earth. They don't negate the overall similarity of the atmosphere when viewed globally. As you contemplate these ideas, drifting toward deeper sleep, imagine yourself floating at different vantage points throughout the cosmos. From each location, you would see galaxies receding in all directions. From each perspective, the universe would appear to expand around you, yet none of these viewpoints is more central than any other. Each is simply a different window on the same cosmic expansion. This equality of perspective invites a certain cosmic humility. We are not at the center of creation, as ancient cosmologies supposed, but neither is any other galaxy or any other observer. The universe does not revolve around anyone. It expands for everyone. Yet there is also a kind of cosmic equality in this understanding. If no location is central, then no location is peripheral either. Every region of space participates equally in the cosmic expansion. Every galaxy rides the same expanding fabric of space-time. Your place in the universe is not privileged, but neither is it diminished. You are exactly where you are, experiencing the same cosmic processes as observers throughout the universe. As we contemplate the night sky, we see stars and galaxies in all directions. Some regions appear denser with stars, others more sparse, but this is largely due to our position within our own galaxy. When we look beyond the Milky Way at the distribution of distant galaxies, we find a remarkable uniformity on the largest scales. This uniformity is another confirmation of the cosmological principle and the absence of a cosmic center. While our particular location in the universe is not special in a geometric sense, it is special in other ways. We find ourselves in a spiral galaxy with abundant heavy elements necessary for complex chemistry and life. We orbit a stable star at just the right distance for liquid water. We evolved on a planet with a protective magnetic field and an atmosphere containing free oxygen. These local conditions make our address in the cosmos remarkable, even if our position relative to the universe's expansion is not. As your consciousness ebbs toward the shores of sleep, carry with you this powerful insight. The universe looks fundamentally the same from anywhere. The cosmic expansion appears centered on every observer. The laws of physics operate identically throughout space. This universality of perspective confirms what theory suggests our universe has no center. Every observer sees expansion all around them, not because they are special, but because that is the nature of cosmic expansion itself. In this vast, expanding cosmos, you are neither at the center nor far from it. You are simply here, now, part of the grand unfolding of space and time. We often hear that the observable universe has a specific size, approximately 46.5 billion light-years in radius. This finite sphere represents all the space from which light has had time to reach us since the Big Bang, taking into account the expansion of space during the light's journey. This might lead us to believe there's a center to this observable sphere, us. After all, we are literally at the center of everything we can see. But this apparent centrality is an observational effect, not a cosmic truth. The observable universe is indeed centered on the observer, whoever and wherever that observer happens to be. If you were located in the Andromeda galaxy, roughly 2.5 million light-years from Earth, you would be at the center of your own observable universe. Your cosmic horizon would extend 46.5 billion light-years in all directions from Andromeda, not from the Milky Way. Your observable sphere would largely overlap with ours, but it would include some regions we cannot see and exclude some regions we can see. This is because the observable universe isn't a physical structure with definite boundaries. It's an observational limit imposed by the finite speed of light, combined with the finite age of the universe. Light from very distant regions simply hasn't had enough time to reach us yet, so those regions remain invisible to us, outside our observable universe. Think of your observable universe as a bubble of visibility that surrounds you wherever you go. If you travel to a distant galaxy, your bubble travels with you. New regions come into view ahead of you, while others disappear behind you. Your location is always at the center of what you can see, but that doesn't make your location cosmically special. The boundary of the observable universe isn't a real wall or edge, it's just the current limit of visibility. Over time, this boundary expands as light from more distant regions reaches us. However, Due to the accelerating expansion of the universe, there are regions of space from which light will never reach us, no matter how long we wait. These regions are permanently beyond our observable universe. Many people mistakenly imagine the Big Bang as an explosion that sent matter flying outward, with the Earth located near the center of this expansion. They picture the observable universe as a bubble expanding into empty space, with us in the middle. But as we've discussed in previous chapters, the Big Bang happened everywhere at once. It wasn't a point-like explosion, but the beginning of space and time throughout the cosmos. The universe is not like an expanding bubble with us at the middle. We are not privileged observers located near the origin point of cosmic history. We are simply located where we are, and our observable universe is centered on us because that's how observation works, not because our location is cosmically central. To illustrate this concept, imagine a large room filled with people, with each person holding a flashlight. In a dark room, each person can see only as far as their flashlight beam reaches. Each person is at the center of their own circle of visibility, but no one is at the center of the room just because they're at the center of what they can see. Similarly, being at the center of our observable universe doesn't place us at the center of the universe as a whole. It merely reflects our location in time and the finite speed of light. Every observer in the cosmos is at the center of their own observable sphere, just as we are at the center of ours. This relativity of cosmic perspective challenges our intuitive understanding of centrality and importance. Throughout history, humans have tended to place themselves at the center of their cosmological models. Ancient geocentric systems put Earth at the center of creation. Later models put the Sun at the center, then our galaxy. Each new discovery has pushed us further from any claim to cosmic centrality. Modern cosmology completes this decentering process by showing that no location is central. Every observer sees the universe expanding around them. Every observer is at the center of what they can observe. This equality of perspective is a profound philosophical insight that emerges from the mathematics and observations of cosmology. The concept of the observable universe also raises fascinating questions about what lies beyond our cosmic horizon. The universe could be finite or infinite in extent. It could be much larger than the part we can see, perhaps hundreds or thousands of times larger, or even infinitely larger. Current evidence suggests the universe is flat or very nearly so, which is consistent with an infinite expanse, but does not prove it. If the universe is finite, it could still lack a center if it has a non-trivial topology. For example, if it's shaped like a three-dimensional torus, similar to a donut shape, but in higher dimensions. In such a universe, traveling far enough in one direction would eventually bring you back to your starting point, much like traveling around the Earth. Such a universe would have no edge and no center. If the universe is infinite, the concept of a center becomes meaningless. An infinite expanse cannot have a middle point. Every location in an infinite universe is surrounded by infinite space in all directions. No position can claim to be central when the universe extends without limit in every direction. But regardless of whether the universe is finite or infinite, the part we can observable universe is definitely finite. It has a well-defined size based on the distance light has been able to travel since the Big Bang, taking into account cosmic expansion. This observable sphere grows slowly over time, as light from more distant regions reaches us. The expansion of the universe affects this growth in complex ways. Initially, the observable universe grows simply because light from more distant regions has time to reach us. But cosmic expansion works against this growth. By stretching space and increasing the distances light must travel. In the current era of accelerated expansion, some regions will permanently remain beyond our observational reach, no matter how long we wait. This creates a kind of cosmic horizontal limit to what we can ever observe or influence. Galaxies beyond this horizon are receding from us faster than the speed of light due to the expansion of space between us. While nothing can move through space faster than light, space itself can expand without this speed limit. This means there are galaxies moving away from us at apparent superluminal speeds when cosmic expansion is taken into account. As you drift toward deeper sleep, contemplate the vastness of the observable universe, a sphere 93 billion light-years in diameter centered on Earth. Within this immense volume are roughly 2 trillion galaxies, each containing billions of stars. Yet this unimaginably large region is likely just a tiny fraction of the universe as a whole. Beyond our cosmic horizon may lie regions we will never see, structures we will never detect, perhaps even other forms of life we will never know. The observable universe reflects our location in time as much as our location in space. An observer 10 billion years ago would have seen a much smaller observable universe because light had less time to travel. An observer 10 billion years in the future would see a different set of galaxies, with many current ones having receded beyond visibility due to cosmic expansion. This temporality of perspective reminds us that our view of the cosmos is a snapshot, not a complete picture. We see the universe not only from where we are in space, but from when we are in time. Our cosmic perspective is shaped by both our spatial location and our temporal moment. The idea that we are at the center of the observable universe, but not at the center of the universe itself, challenges us to distinguish between observation and reality. What we see is limited by our vantage point. The true extent and structure of the cosmos likely exceeds anything we can directly observe. Yet through science, mathematics, and careful reasoning, we can infer properties of the universe beyond our direct observation. We can deduce that the universe has no center. We can calculate that space expands uniformly. We can determine that the laws of physics apply consistently throughout the cosmos. These insights allow us to transcend the limitations of our observational bubble and grasp the larger truths of cosmic structure. As your thoughts grow more diffuse and sleep approaches, imagine the vastness extending beyond your observable horizon. Countless galaxies, unseen and unseeable, continue the patterns we observe in our local region. Space stretches silently in all directions, carrying distant worlds away at ever-increasing speeds. The universe continues its expansion, indifferent to observers, with no special regions and no privileged center. In this boundless cosmos, you float in your small observable sphere, not at the center of everything, but at the center of everything you can see, and that, after all, is enough. The geometry of space itself plays a crucial role in understanding why the universe lacks a center. When we think about geometry, we often imagine flat surfaces, straight lines, and simple shapes from our everyday experience. But the universe operates on principles that extend beyond our intuitive understanding of spatial relationships. In cosmic geometry, we must consider how space itself can curve and how this curvature affects the concept of centrality. According to current observations and measurements, our universe appears to be flat, or very nearly so. In a flat universe, parallel lines remain parallel forever, and the angles of a triangle sum to exactly 180 degrees. This flatness has important implications for the overall structure of the cosmos and reinforces the absence of a central point. But even if space were curved, it could still lack a center. Consider a simple two-dimensional analogy: the surface of a sphere, like the Earth. This surface is clearly curved. It has what mathematicians call positive curvature. If you draw a large triangle on the Earth's surface, using segments of great circles, the shortest paths between points, you'll find that the angles sum to more than 180 degrees. Parallel lines on a sphere eventually converge, like lines of longitude meeting at the poles. Yet despite this curvature, the Earth's surface has no center on the surface itself. You cannot point to any location on the globe and identify it as the central point of the surface. The center of the Earth exists, but it lies below the surface, in a dimension that a hypothetical two-dimensional being living on the surface cannot access or directly experience. Similarly, a saddle shape exhibits negative curvature, where parallel lines diverge and the angles of triangles sum to less than 180 degrees. Yet a saddle shape also lacks a central point. Curvature does not necessitate centrality. Our three-dimensional space could be similar, potentially curving in ways that a hypothetical fourth spatial dimension would be needed to fully visualize. If the universe has positive curvature, like a hypersphere, negative curvature, like a hyperbolic space, or even a more complex topology, it can still lack a geometric center. The general theory of relativity, Einstein's revolutionary framework for understanding gravity, tells us that space isn't just a static backdrop against which cosmic events unfold. Space is dynamic. It bends, warps, and stretches in response to matter and energy. Massive objects like stars and planets create dimples in the fabric of space-time, and this curvature is what we experience as gravity. On a cosmic scale, the overall distribution of matter and energy determines the large-scale geometry of the universe. If the average density of matter and energy exceeds a critical value, the universe would have positive curvature and be finite in volume, though still without a boundary. If the density exactly matches the critical value, the universe would be flat and potentially infinite. If the density falls below the critical value, the universe would have negative curvature and also be infinite. Precision measurements of the cosmic microwave background radiation and other observations suggest that our universe is flat within the margin of error of our instruments. The density of matter and energy appears to be remarkably close to the critical value required for flatness. This flat geometry extends as far as we can observe, though we cannot definitively determine whether this flatness continues indefinitely beyond our cosmic horizon. In a flat, infinite universe, the concept of a center becomes meaningless. You cannot have a middle point of an infinite expanse. Every location is surrounded by infinite space in all directions. No position can claim to be more central than any other. Even in a finite universe with positive curvature, like a higher dimensional analog of a sphere's surface, there would be no center within the universe itself. Such a universe would be finite in volume, but have no boundary or edge. Its center would exist in a higher dimension, not directly part of the universe, similar to how the center of a sphere is not on its surface. The geometry of space creates a framework that defines how objects move, how structures form, and how light travels. But this geometry does not require or generate a special central point. Instead, it creates a vast arena where cosmic evolution unfolds uniformly across all regions. Consider how we navigate on Earth. We use coordinate systems like latitude and longitude to specify locations. These coordinates are convenient human inventions, not physical features of the planet. The equator isn't a visible line painted across Earth's surface. The prime meridian isn't a natural boundary, but a human-designated reference line passing through Greenwich, England. Similarly, in cosmology, we use coordinate systems to map the universe, but these are mathematical conveniences, not physical realities. We might place ourselves at the origin of our coordinate system, but this doesn't make our location physically special. Another observer in a distant galaxy could establish a different coordinate system centered on their location, and both would be equally valid. This relativity of coordinate systems reflects a deeper truth about the universe. Position itself is relative. There is no absolute framework against which all motion and location can be measured. This principle, formalized in Einstein's theories of relativity, undermines any notion of an absolute center to the cosmos. The mathematics of general relativity, which describes the large-scale structure and dynamics of the universe, is explicitly designed to be covariant, meaning its equations take the same form regardless of the coordinate system used. This mathematical property reflects the physical reality that the laws of nature don't depend on location or perspective. They work the same way everywhere and for everyone. In Einstein's field equations, which relate the geometry of spacetime to the distribution of matter and energy, there is no term or concept that designates a cosmic center. These equations describe a universe that can expand, contract, or remain static, but they do not single out any location as special or central. The solutions to these equations that match our observations describe a uniform expansion that looks the same from any vantage point. At the quantum level, the uncertainty principle tells us that position itself is not an absolute, precisely definable property for subatomic particles. Particles exist in probability distributions rather than exact locations. This quantum fuzziness at the smallest scales reinforces the absence of absolute position at the foundations of physics. Even the concept of now is relative in Einstein's universe. Different observers moving at different velocities or in different gravitational fields experience time differently. There is no universal, synchronized cosmic clock that all observers would agree on. This relativity of simultaneity further undermines the notion of a universal center, which would require a privileged reference frame. As you drift deeper towards sleep, imagine the vast cosmic geometry extending in all directions. Space curves gently around massive objects but maintains an overall flatness across the largest scales. Galaxies and galaxy clusters form a cosmic web within this geometric framework, but this structure doesn't revolve around a central hub. The web extends uniformly, with similar patterns repeating across billions of light years. Your place in the universe is not central in a geometric sense, but neither is anyone else's. Our location is simply one among countless points in a vast, possibly infinite expanse. The laws of physics, the properties of particles, the fundamental forces, these are the same where you are, as they are in galaxies billions of light years distant. This universality suggests a kind of cosmic equality. No location is privileged by the geometry of space. No position confers special status or importance. We are not at the center of the universe, but in a universe without a center, no one else is either. We are simply here, embedded in the same expanding field as everything else, subject to the same physical laws, part of the same cosmic story. The geometry of the universe defines how things move and interact within it, but it doesn't define importance or meaning. Those are qualities we bring to our experience of the cosmos. Though we may not be geometrically central, we can still be cosmically significant through our capacity for observation, understanding, and appreciation of the universe's vast and elegant structure. In the next chapter, we'll explore the implications of an infinite universe and how infinity further challenges the concept of centrality. We'll see how in an endless cosmos, the idea of a middle becomes not just difficult but logically impossible. But for now, rest in the knowledge that the geometry of space creates a vast, uniform arena for cosmic evolutionary geometry that curves without centralizing, that shapes without favoring, that extends without privileging any particular location over others. If the universe is truly infinite and, current evidence suggests, it might, then the concept of a center becomes not just difficult to define, but mathematically impossible. An infinite expanse, by definition, extends without limit in all directions. Every location, no matter where you travel in this boundless cosmos, is surrounded by infinite space on all sides. There can be no middle point to infinity. This realization takes our journey of cosmic decentering to its logical conclusion. If ancient cosmologies placed Earth at the center of creation, and early modern astronomy moved the center to the Sun, and later discoveries pushed the center outward to the Milky Way, and then dissolved it entirely in an expanding universe, the concept of infinity removes even the theoretical possibility of a central location. To understand why infinity precludes centrality, consider a simple one-dimensional example: an infinite line extending forever in both directions. Where is the center of this line? You might be tempted to place a marker at some arbitrary point and call it the origin, or zero, but this is merely a coordinate convention, not an inherent feature of the line itself. Any point on an infinite line has exactly the same geometric status as any other infinite distance, extends in both directions from every point. Extending this to our three-dimensional universe, if space is infinite in all directions, then every location is precisely in the same geometric situation, surrounded by limitless space extending forever in all directions. No location can claim to be more central than any other when all are infinitely distant from any potential edge, which doesn't exist in the first place. The infinite universe scenario represents one possibility for cosmic geometry, and it aligns with current observations, suggesting that space is flat, or very nearly so. A perfectly flat universe that extends indefinitely would indeed be infinite in volume, containing an unlimited number of galaxies, stars, and potentially other Earth-like planets. If this is the case, our observable universe, the spherical region from which light has had time to reach us since the Big Bang, represents an almost infinitesimally small fraction of the total cosmos. It would be like a single grain of sand on an endless beach, or a single atom in an ocean that stretches forever. The 2 trillion or so galaxies we can potentially observe would be just the tiniest sample of an unlimited number of galaxies populating the universe beyond our cosmic horizon. In such an infinite universe, the question, where did the Big Bang happen, takes on a different meaning. The Big Bang wasn't an explosion at a point within pre-existing space. It was the beginning of space and time throughout an already infinite expanse. Every region of today's universe was present in the hot, dense early state, compressed together with all other regions. As space expanded, these points moved apart, but none represented the original center because there was no center to an infinite beginning. This concept challenges our intuition profoundly. We naturally think of beginnings as localized events, starting from specific points and spreading outward. But cosmic evolution defies this pattern. An infinite universe doesn't expand from a central point, but expands everywhere simultaneously. Even if the universe is not infinite, but instead finite, it could still lack a center if it has a non-trivial topology. Imagine the universe as a three-dimensional analog of a torus the shape of a donut. On the surface of a donut, you can travel in a straight line and eventually return to your starting point without ever reaching an edge. Such a surface is finite in area, but has no boundary and no center point on the surface itself. Similarly, our universe could be finite in volume while having no edge and no center. It could loop back on itself in complex ways that are difficult to visualize, but mathematically coherent. In such a universe, traveling far enough in one direction would eventually bring you back to your starting point, much like traveling around the Earth. Cosmologists refer to this possibility as a multiply-connected universe, where space has a non-trivial global topology. While a flat universe that extends indefinitely would be infinite, a flat universe could also be finite if its topology allows space to connect back to itself, like a three-dimensional analog of a video game, where exiting one side of the screen brings you back in from the opposite side. Observations thus far haven't detected any signs of such cosmic wraparound, which would appear as multiple images of the same distant objects seen in different directions. But the universe could be so large that the distance needed to observe this wraparound effect exceeds our current observational capabilities. Whether infinite or finitely curved, whether simply or multiply connected, in all these geometric scenarios, the universe still lacks a center. The absence of centrality is a robust feature across all plausible cosmic geometries consistent with our observations. In both infinite and curved space, the idea of center fades from physical reality into mere convention. What matters instead is structure, motion, and distribution, the patterns formed by matter and energy within the cosmic framework, not its overall shape or central point. This raises profound philosophical questions about our place in the cosmos. If the universe has no center and potentially extends infinitely, what does this mean for humanity's significance? Are we rendered even more marginal in an infinite expanse than in merely a vast one? Some find this perspective troubling, even existentially challenging. If the universe is boundless, with no special central region, and our observable portion is just an infinitesimal fraction of the whole, doesn't this make us utterly insignificant? But another perspective sees profound meaning in this cosmic democracy. In a universe with no center, no location is privileged over any other. Each region, each galaxy, each planet exists on equal cosmic footing. The absence of geometric hierarchy suggests a kind of universal equality, not that any location is special, but that every location is equally part of the cosmic whole. Moreover, in an infinite universe, the probability approaches certainty that everything physically possible occurs somewhere and, indeed, occurs an infinite number of times. This suggests that somewhere in the cosmic expanse, there are likely other planets remarkably similar to Earth, perhaps even with beings remarkably similar to humans, contemplating their own place in the infinite cosmos. This idea of cosmic reflection, that an infinite universe would contain infinite repetitions and variations of everything we know, raises fascinating questions about identity, uniqueness, and the nature of possibility. Are we unique if versions of us exist elsewhere? Does infinity make everything mundane by making everything inevitable, or does it elevate everything by making nothing truly lost in the grand scheme? These philosophical questions touch on the limits of science. While physics can describe the structure and evolution of an infinite universe, it cannot tell us what such infinity means for human values, purpose, or significance. These interpretations belong to philosophy, theology, and personal reflection. From a scientific perspective, what we can say is that wherever you stand in a potentially infinite universe, space continues in all directions. There is no edge to reach, no boundary to cross, no central region toward which all things gravitate. Every direction offers the same endless progression of galaxies, clusters, and cosmic filaments, a pattern that repeats with infinite variations throughout limitless space. This vast, possibly infinite nature of the universe also affects how we think about cosmic origins. The Big Bang Theory describes how our observable universe evolved from a hot, dense state to its current form, but it doesn't necessarily describe the beginning of everything that exists. If space is truly infinite, then the Big Bang represents the beginning of our observable region, but infinite space could have existed in that initial hot, dense state, with no absolute beginning. Some cosmological models propose a multiverse, larger reality containing many universes, perhaps infinitely many. In such scenarios, our universe would be just one bubble in an endless sea of cosmic bubbles, each with potentially different physical laws, constants, and histories. This multiplies infinity upon infinity, suggesting a reality far vaster and more diverse than even our infinite universe. But even in a multiverse, the principle of no center would likely still apply. Just as our universe has no special central point, the multiverse would have no privileged universe at its middle. Each cosmic bubble would be equally part of the greater whole, with none occupying a geometrically special position. As you continue to drift toward deeper sleep, try to release your mental attachment to the idea of centrality. Our intuitions about centers come from our evolutionary history and daily experience with finite objects that have clear midpoints. But the cosmos operates on principles that transcend these limited intuitions. Imagine yourself floating in infinite space. In front of you, galaxies extend forever. Behind you, the same. Above, below, to your left, to your right, in every possible direction, cosmic structures continue without end. There is no special direction that leads to a central hub or an outer boundary. There is only endless space filled with endless variations of stars, galaxies, and clusters. In this infinite expanse, your location is neither central nor peripheral. These concepts lose meaning when applied to infinity. Instead, your position is simply unique, the particular vantage point from which you observe the endless cosmos. No one else in the universe, not even a hypothetical, identical copy of you elsewhere in infinity, occupies exactly the same location and sees exactly the same view. This uniqueness of perspective gives every observation point a kind of significance. While not geometrically special, each location provides a singular window on the universe, a unique compilation of views and experiences. Your cosmic address may not be central in any absolute sense, but it is uniquely yours. Consider how this perspective shifts our understanding of cosmic identity. In a finite universe with a center, location could confer special status. Being closer to or farther from the middle would make a position distinctive. But in an infinite or centerless universe, what distinguishes one region from another is not its position relative to some central point, but the particular constellation of matter, energy, and events that unfolds there. Our Milky Way galaxy isn't special because of where it sits in the cosmic framework, but because of its specific characteristics, its spiral structure, its particular mix of stars, its unique history of formation and evolution. Earth isn't significant because of its position in the absolute sense, but because of the remarkable emergence of life and consciousness that occurred here. In an infinite universe, significance comes not from position, but from process, not from where something is, but from what happens there. The development of complexity, the emergence of life, the evolution of consciousness, these processes would be remarkable wherever they occur, regardless of cosmic address. The concept of an infinite universe also challenges how we think about cosmic diversity. If space extends forever and contains an infinite number of galaxies, then the probability approaches certainty that every possible configuration of matter permitted by the laws of physics occurs somewhere and, indeed, occurs infinitely many times. This suggests that somewhere in the infinite cosmos, there exist planets remarkably similar to Earth, perhaps even with beings similar to humans, contemplating their own place in infinity. Some may be reading books or listening to narrations about why the universe has no center, just as you are now. This idea of cosmic repetition raises profound questions about uniqueness and identity. If versions of us exist elsewhere, are we truly unique? Does infinity make everything mundane by making everything inevitable, or does it elevate everything by making nothing truly lost? These questions touch on the boundary between physics and metaphysics. Science can describe the structure and properties of an infinite universe, but the meaning and significance we assign to infinity belongs to philosophy and personal interpretation. What we can say scientifically is that infinity transforms how we understand our place in the cosmos. We are neither central nor peripheral in an infinite universe. These concepts simply don't apply. We are simply here, in our particular region of endless space, experiencing our particular moment in cosmic evolution. This perspective offers both humility and dignity. Humility, because we recognize that our location confers no special cosmic status. Dignity, because we understand that in a universe without a center, every location stands on equal cosmic footing. Our significance comes not from where we are, but from who we are and what we do with our unique window on the infinite. As sleep approaches and your thoughts grow more diffuse, let go of the need to place yourself at any particular position in the cosmic hierarchy. In a universe without a center, there is no hierarchy of location. There is only the vast tapestry of space and time, with each thread, each galaxy, each star, each planet, each living being woven into the infinite pattern. Wherever you find yourself in this boundless cosmos, you are exactly where you are, not at the center, not at the periphery, just here, now, part of the infinite whole. And in that simple fact lies both cosmic truth and personal peace. In the unfolding story of an infinite universe, your chapter is neither the beginning nor the end, neither the most important nor the least. It is simply your unique perspective, a singular experience of the limitless cosmos, and in a universe without a center, that is enough. As your consciousness ebbs toward the shores of sleep, imagine space extending forever in all directions. Stars beyond stars, galaxies beyond galaxies, clusters beyond cluster-san, endless progression of cosmic structures. In this infinite expanse, you float, neither central nor marginal, simply present. And in that presence, you find your place no at the center of everything, but at the center of your own experience of everything. Not significant because of where you are, but significant because you are here at all, a conscious witness to the infinite. Tomorrow, we will continue our exploration of the centerless cosmos, examining how the language we use sometimes misleads us into thinking of the universe as expanding from a central point. We'll see how our words can create conceptual barriers to understanding the true nature of cosmic expansion. But for now, rest in the peaceful awareness that you float in a universe that extends without limit and without center, a cosmos where every point is simply part of the infinite whole, no more or less central than any other. In this boundless cosmic sea, you drift toward dreams, carried on currents of expanding space. The stars wheel overhead, the galaxies recede in the distance, and space stretches silently in all directions. There is no center to find, no special place to seek. There is only the vast, expanding fabric of the universe, and your consciousness flickering within it like a star, unique, not because of where it shines, but because it shines at all. The absence of a cosmic center doesn't diminish your significance. Indeed, it enhances it. In a universe with a privileged center, most locations would be secondary, peripheral, less important than the central hub. But in a universe without a center, especially an infinite one, every location exists on equal geometric footing. None is privileged by position. All participate equally in the cosmic expansion and evolution. This democratic cosmos invites us to find meaning not in special placement, but in special processes, the emergence of complexity, the development of life, the awakening of consciousness, the pursuit of understanding. These remarkable phenomena would be significant wherever they occur, regardless of cosmic address. As your thoughts grow more diffuse and sleep draws nearer, release any lingering attachment to cosmic centrality. Let go of the need to be specially positioned in the universe. Embrace instead the freedom of a cosmos without a center, a universe where every location is simply itself, neither elevated nor diminished by its position relative to other points. In this infinite or curved space, the idea of center dissolves into meaninglessness. What remains is the simple fact of your existence, your awareness, your participation in the cosmic unfolding. Not central, but connected. Not at the middle, but in the midst. Not positioned at a special spot, but living through a special moment, the development of consciousness, capable of comprehending the very infinity that contains it. Rest now in that awareness, allowing sleep to carry you into dreams that, like the universe itself, have no center and no boundary, only the endless play of possibilities unfolding in the theater of consciousness. Tomorrow we continue our cosmic journey, but tonight we float in the infinite, centerless sea of stars, perfectly positioned in the exact spot we occupy, neither central nor peripheral, simply here, now, amid the vast and endless cosmos. Sometimes, the greatest barriers to understanding the universe aren't the complex mathematics or the vast distances involved, but something much more fundamental, the language we use to describe cosmic phenomena. Our words often carry hidden assumptions that can lead us astray when contemplating the nature of the cosmos. Nowhere is this linguistic limitation more apparent than in discussions about the universe's lack of a center. We speak casually of expansion from the Big Bang, as if it were an explosion emanating from a particular location. We describe space as stretching out or growing, implying a process occurring within a larger framework. We talk about the universe being created at a specific moment, suggesting a beginning point in both time and space. These phrases feel natural to us because they mirror our everyday experiences with objects that grow outward from origins, explosions that radiate from central points, and creations that begin somewhere specific. But the universe defies these familiar patterns. It isn't expanding from anywhere, it's expanding everywhere. The Big Bang wasn't a location, but an event that encompassed all of existence. Space isn't stretching into anything, it's simply stretching. Our language struggles to capture these concepts because our vocabulary evolved to describe middle-sized objects, moving at middle-sized speeds within already existing space, not the behavior of space itself on cosmic scales. Even calling the beginning of the universe a bang is profoundly misleading. The term conjures images of an explosion, violent, noisy eruption from a specific point. But the beginning of the universe wasn't like a firecracker detonating in an empty room. It was more like the appearance of the room itself, with all its contents already distributed throughout, albeit in an incredibly hot, dense state. The name Big Bang actually originated as something of a dismissive joke. Astronomer Fred Hoyle, who favored an alternative steady-state theory of the universe, coined the term during a radio broadcast in 1949, intending it to sound absurd. These theories were based on the hypothesis that all matter in the universe was created in one Big Bang at a particular time in the remote past, he said, using the term to make the idea sound implausible. Despite Hoyle's intentions, the catchy name stuck, and now we're left with a term that inadvertently reinforces the incorrect notion of a central explosion. A more accurate but less dramatic name might be the everywhere stretch or the cosmic beginning. These terms better capture the nature of the event without implying a central eruption point. But Big Bang remains firmly established in both scientific literature and popular culture, so cosmologists must constantly clarify what they actually mean by this potentially misleading term. Our language shapes our thought, and our thought shapes how we interpret and understand the universe. When we use phrases like expanding from the Big Bang, we unconsciously reinforce the incorrect mental model of an explosion from a central point. This isn't merely a semantic quibble, it fundamentally affects our ability to grasp the true nature of cosmic evolution. Consider how we describe cosmic distances. We say one galaxy is 13 billion light-years away. This statement seems straightforward, but it actually conceals a complex reality. That galaxy isn't simply at a fixed distance of 13 billion light-years. Space has been expanding during the entire time its light has been traveling toward us. The galaxy is now much farther away than 13 billion light-years, perhaps 30 billion light-years or more, depending on the expansion history of the universe. But we see it as it was 13 billion years ago, when the light began its journey and when the galaxy was indeed much closer to us. This complexity is difficult to capture in simple language. We could say, we observe a galaxy whose light has been traveling for 13 billion years, which is now approximately 30 billion light-years away due to cosmic expansion. But such precision quickly becomes cumbersome in everyday discussion. So we default to simpler expressions that inadvertently reinforce incorrect models of cosmic structure and evolution. Even seemingly innocent phrases like the edge of the universe or the boundary of space mislead us. They suggest that the universe has an outside, a perimeter that encloses space. But current understanding suggests that the universe either continues indefinitely or curves back on itself without a boundary. There is no edge to reach, no outside to access. Space may be finite or infinite, but either way, it doesn't have a border separating it from something else. When we describe the uniformity of the universe on large scales, we often say the universe is homogeneous and isotropic. These technical terms mean the universe looks roughly the same in all directions and at all locations when viewed at sufficiently large scales. But these precise words aren't part of everyday vocabulary, so we resort to more familiar terms that can distort understanding. We might say the universe is symmetric or balanced, but these words can imply a central point around which this symmetry is organized. True cosmic homogeneity and isotropy require no center. In fact, they are most naturally realized in a centerless universe. The phrase, the observable universe itself, can be misinterpreted. It sounds like a specific region of a larger whole, with us at the middle of this observable bubble. While this is technically true, we can only see light that has had time to reach us since the Big Bang. It can reinforce the incorrect notion that our location is cosmically special. Every observer in the universe has their own observable sphere centered on them. The phrase doesn't indicate that we occupy a privileged position. It simply acknowledges the finite speed of light and the finite age of the universe. Our descriptions of time also subtly reinforce centralized thinking. We speak of events happening after the Big Bang, as if the Big Bang were a localized event in pre-existing time. But time itself began with the Big Bang. There was no before, at least not in any sense we can access through observation. Time didn't pre-exist the universe. It emerged with it, just as space did. Saying something happened after the Big Bang is like saying something is north of the North Pole. It assumes a framework that doesn't exist. Even the way we visualize the early universe can mislead. When we see images depicting the first moments after the Big Bang, they often show a small, dense ball of energy exploding outward. But this representation is fundamentally inaccurate. The early universe wasn't small, it contained all of space. It may have been incredibly dense, but it wasn't a small object within a larger void. It was everything that existed, already distributed throughout all of space, which was itself in a highly compressed state. These linguistic and conceptual challenges aren't unique to discussions of cosmic centrality. They appear throughout cosmology. For instance, when we discuss the accelerating expansion of the universe, we often say that dark energy pushes space apart. This phrasing makes it sound like dark energy is a force acting on space from outside. But current understanding suggests that dark energy is a property of space itself, not something external pushing outward, but an intrinsic tendency of space to expand at an increasing rate. Our language struggles to capture phenomena that don't conform to our everyday experiences of objects pushing other objects. Similarly, when discussing cosmic inflation, the theorized period of extremely rapid expansion in the first fraction of a second after the Big Bang, we often describe it as an exponential growth spurt. This familiar term suggests a localized process, like a plant suddenly shooting upward. But inflation, like all cosmic expansion, happened everywhere simultaneously. It wasn't a growth from a center, but a universal stretching of space itself. Our language is shaped by our evolutionary history and daily experiences. For most of human existence, our ancestors dealt with middle-sized objects moving at moderate speeds within already existing space. They didn't need words to describe the behavior of space itself or phenomena occurring at cosmic scales. As a result, our vocabulary is better suited to describing apples falling from trees than galaxies receding due to the expansion of space. Even the basic spatial prepositions we use, in, on, at, from, to assume a framework of static space within which objects move or events occur. But when discussing the behavior of space itself, these prepositions can become misleading. The universe isn't expanding into anything. Galaxies aren't moving through space when referring to the recession due to expansion. The Big Bang didn't happen at a location. Our basic linguistic tools struggle to capture these concepts accurately. The phrase, "the universe is expanding," itself requires careful interpretation. In everyday language, when something expands, it gets larger relative to the space it occupies. A balloon expands into the room around it. A gas expands to fill its container, but the universe doesn't expand into anything. It is all there is. Its expansion refers to the increasing distances between objects within it, not to its growth relative to something outside. Some languages may be better equipped than others to discuss these concepts. Languages with different grammatical structures or semantic categories might find it easier to express the idea of expansion without implying a center. But all human languages evolved in the context of everyday experience, not cosmic reality, so all face limitations when describing phenomena that operate outside the realm of ordinary perception. Scientists address these linguistic limitations by developing precise mathematical models that don't rely on potentially misleading verbal descriptions. The equations of general relativity that describe cosmic expansion don't include a central point or a special origin. They represent space as expanding uniformly, with every point moving away from every other at a rate proportional to the distance between them. This mathematical precision avoids the ambiguities and hidden assumptions of everyday language. But even scientists must translate these mathematical models into words when communicating with each other and the public. And in this translation, subtle misconceptions can creep in. A physicist might say the universe is expanding everywhere, knowing this means every point is moving away from every other due to the stretching of space itself. But a listener might hear this and still picture an explosion from a central point, with matter flying outward into pre-existing emptiness. This gap between mathematical precision and verbal approximation creates a persistent challenge in cosmology education. Educators must repeatedly confront and correct the mistaken mental models that our language naturally produces. They must find ways to convey concepts that our vocabulary wasn't designed to express, and our intuitions weren't evolved to grasp. Visual aids and analogies can help bridge this gap, but they too have limitations. The popular balloon analogy for cosmic expansion, where galaxies are represented by dots on the surface of an inflating balloon, effectively shows how every point can move away from every other without a center. But it can also reinforce the incorrect notion that the universe has a higher dimensional outside and a definite boundary, like the balloon's surface. Computer simulations provide more accurate visualizations of cosmic expansion, showing how structures form and evolve in a universe without a center. These models start with nearly uniform distributions of matter and apply the laws of physics to evolve them forward in time. From any vantage point in such a simulation, an observer would see all other points receding, exactly as we observe in our actual universe. But even the most sophisticated visualization or analogy can't fully escape the limitations of our conceptual framework. We think in terms of objects moving through space because that's the reality we evolved to perceive. The idea that space itself can stretch, and that this stretching requires no center and no external void to expand into, remains profoundly counterintuitive. Perhaps the most honest approach is to acknowledge these linguistic and conceptual limitations directly. When we say the universe has no center, we're not just making a statement about cosmic geometry. We're also challenging our intuitive understanding of what it means for something to begin, to expand, to exist. We're pushing against the boundaries of language itself, trying to describe a reality that doesn't conform to the assumptions built into our vocabulary. This challenge isn't unique to discussions of cosmic centrality. It appears throughout modern physics, from quantum mechanics to general relativity. Quantum phenomena like superposition and entanglement defy our everyday understanding of how objects behave. Relativistic effects, like time dilation and length contraction, contradict our intuitive sense of time and space. In each case, our language struggles to capture concepts that operate outside the realm of ordinary experience. As you drift toward deeper sleep, consider how your understanding of the universe is shaped not just by scientific evidence, but by the words and metaphors used to describe that evidence. The phrases expanding universe and Big Bang conjure certain images in your mind images that may unconsciously reinforce the incorrect notion of a cosmic center. Try to set aside these linguistic limitations and picture the universe as it truly is, a vast fabric of space expanding uniformly, with every region moving away from every other, not because any point is special, but because expansion is the nature of space itself. The beginning wasn't a localized event, but a universal one, occurring everywhere simultaneously. The growth of the cosmos isn't an outward radiation from a central point, but a stretching that happens equally in all regions. This view requires us to transcend the constraints of language and embrace a perspective that doesn't rely on familiar spatial concepts. It asks us to see the universe not through the lens of everyday experience, but through the more accurate framework of modern cosmology. It challenges us to recognize how our words can mislead us and to search for clearer ways to express cosmic realities. In the silence of the night, as your thoughts grow more diffuse and sleep approaches, let go of the mental pictures that language has created. Release the image of an explosion radiating from a center. Abandon the notion of the universe growing outward into empty space. Instead, embrace the subtler truth, a cosmos that expands everywhere at once, that began everywhere simultaneously, that has no center because it needs none. The universe doesn't revolve around a hub. It doesn't spiral out from an origin. It doesn't grow from a seed planted in the void. It expands universally, with each region receding from every other, not due to motion through space, but due to the stretching of space itself. This is a reality that our words struggle to capture, but that mathematics describes precisely and observations confirm consistently. As consciousness fades and dreams begin to form, carry this perspective with you. You are not at the center of everything, but neither is anyone else. You float in a universe that expands without preference for any location, that evolved from a beginning that happened everywhere at once, that continues to grow not from a central point, but throughout its entire vast expanse. In this centerless cosmos, your position may not be geometrically special, but your awareness, your ability to comprehend these very concepts, remains remarkable regardless of where it exists in the expanding cosmic fabric. Tomorrow, we'll explore how the cosmic microwave background radiation, the oldest light in the universe, provides some of our strongest evidence for a universe without a center. We'll see how this ancient afterglow of the Big Bang shows a remarkable uniformity across the sky, confirming the homogeneity and isotropy of the early universe and supporting the absence of a privileged central location. But for now, rest in the knowledge that the linguistic barriers to understanding cosmic centrality can be overcome, that the universe can be comprehended even when our words falter, and that the truth of a centerless cosmos can be grasped despite the limitations of language. The words we use shape the reality we perceive. By becoming aware of how our language can mislead us in cosmology, we take the first step toward a deeper, more accurate understanding of our place in the universe. As sleep envelops your consciousness, let this awareness remain. The cosmos is not as our words often describe it, but something more subtle, more uniform, more democratically structured. A universe not centered on any particular point, but expanded equally in all regions and evolving according to the same physical laws throughout its vast, possibly infinite expanse. The cosmic microwave background radiation, often abbreviated as the CMB, stands as one of the most powerful pieces of evidence for the universe's lack of a center. This ancient light, discovered accidentally in 1964 by Arno Penzias and Robert Wilson, provides us with the oldest image of the cosmos we can obtain, a snapshot from when the universe was just 380 years old, less than 0.003% of its current age. What this primordial radiation tells us about cosmic structure has profound implications for understanding why the universe has no center. The CMB is, in essence, the afterglow of the Big Bang, the first light that could freely travel through space, once the universe had cooled enough for electrons to combine with protons to form neutral hydrogen atoms. Before this moment, the universe was an opaque plasma, with photons constantly scattering off free electrons, unable to travel far. But as the universe expanded and cooled, reaching a temperature of about 30 degrees Kelvin, these electrons and protons combined to form neutral atoms in a process called recombination. Suddenly, light could travel unimpeded through space, and that light, stretched by cosmic expansion over 13.8 billion years, reaches us today as microwave radiation. When we map this background radiation across the entire sky, we find something remarkable. It is astonishingly uniform. After accounting for our own motion through space, which creates a slight Doppler shift in the radiation, making it appear slightly hotter in the direction we're moving and slightly cooler in the opposite direction, the temperature of this ancient light varies by only about 1 part in 100, 0 across the entire celestial sphere. This extraordinary uniformity tells us something profound about the early universe. It was remarkably homogeneous, with nearly identical conditions everywhere. If the universe had a center from which expansion proceeded, we would expect to see systematic differences in the CMB, depending on which direction we looked. Regions closer to this hypothetical center would have different properties than regions farther away. The CMB would show a gradient or pattern pointing toward or away from a special direction. But we observe no such pattern. Once we account for our own motion, the CMB looks essentially the same in every direction. This uniformity is so striking that it actually created a puzzle for cosmologists, the horizon problem. Regions of the CMB on opposite sides of the sky were never in causal contact with each other. Light from one region wouldn't have had time to reach the other, given the age of the universe at the time of recombination. So why are they at virtually identical temperatures? The theory of cosmic inflation was proposed partly to solve this problem, suggesting that an extremely rapid expansion in the first tiny fraction of a second after the Big Bang could have allowed regions to be in contact before being stretched far apart. But for our current discussion, the key point is that the CMB's extraordinary uniformity confirms two fundamental properties of the universe: isotropy, looking the same in all directions, and homogeneity, having the same properties at each location. These twin properties form what cosmologists call the cosmological principle, the foundational assumption that, on the largest scales, the universe has no special places or directions. This principle directly contradicts the notion of a cosmic center. A universe with a center would, by definition, have a special location and would look different depending on direction. The fact that the CMB appears nearly identical in all directions, with only tiny random fluctuations, tells us that the universe doesn't have a preferred orientation or a central hub from which everything expanded. The tiny temperature variations that do exist in the CMB, those 1 part in 100, zero differences, are themselves distributed isotropically across the sky. There is no pattern to these fluctuations that would indicate a preferred direction or central point. Instead, they represent the seeds of cosmic structures, lightly denser regions that would eventually grow into the galaxies, clusters, and superclusters we see today. Their random distribution across the sky further confirms the absence of a cosmic center. When we analyze these temperature fluctuations in detail, we find that they match precisely what we would expect from quantum fluctuations in the early universe: random variations in density that were stretched to cosmic scales during inflation. The statistical properties of these fluctuations, their size distribution, and correlation patterns provide some of our strongest evidence for the standard model of cosmology, which includes the principle that the universe has no center. Advanced satellites like NASA's Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck mission have mapped these fluctuations with increasing precision, allowing cosmologists to measure the fundamental parameters of the universe with remarkable accuracy. The patterns in the CMB tell us about the universe's age, composition, geometry, and expansion history. They confirm that space is nearly flat, Euclidean, on the largest scales, and that the universe is dominated by dark energy and dark matter, with ordinary matter making up just a small fraction of the total. But perhaps most importantly for our discussion, these measurements confirm beyond reasonable doubt that the universe is isotropic and homogeneous on large scales, with no evidence for a special central location. The CMB looks essentially the same no matter which direction we look, once we account for our own motion through space and the small random fluctuations that seeded cosmic structure. This symmetry in the CMB provides perhaps the strongest observational evidence that the universe has no center. If there were a center from which everything expanded, we would see a distinctive pattern in the background radiation pointing toward or away from that special direction. The absence of such a pattern confirms that expansion happens uniformly throughout space, with no preferred origin point. Imagine viewing a true explosion, like a firework detonating in the night sky. If you were to take a snapshot of the expanding debris at a particular moment, you would see a clear pattern, denser near the center, more diffuse toward the edges, with velocities increasing with distance from the origin point. But the CMB shows no such pattern. Its uniformity tells us that the Big Bang wasn't an explosion in space, but an event that happened everywhere simultaneously. The CMB not only confirms the isotropy of space, but also gives us insight into its geometry. By measuring the angular size of the temperature fluctuations, cosmologists can determine whether space is flat, positively curved, like the surface of a sphere, or negatively curved, like a saddle shape. These measurements indicate that space is flat, or very nearly so, within the margins of observational error. This flatness is consistent with cosmic inflation and supports the possibility that the universe may be infinite in extent, further undermining the concept of a cosmic center. When we combine CMB observations with other cosmological data such as measurements of the distribution of galaxies, the brightness of distant supernovae, and the abundance of light elements from Big Bang nucleosynthesis, we get a consistent picture of a universe expanding uniformly from an initial hot, dense state with no special central point. All these independent lines of evidence converge on the same conclusions, giving us high confidence in the standard cosmological model, which includes the principle that the universe has no center. But the CMB doesn't just tell us about the large-scale structure and evolution of the universe. It also reveals details about the early universe that have profound implications for our understanding of cosmic origins. The pattern of temperature fluctuations contains information about the physics of the first moments after the Big Bang, the relative abundances of ordinary matter, dark matter, and radiation, the process of inflation that may have caused the universe to expand exponentially in its earliest instance, and the quantum fluctuations that seeded the formation of all structure we see today. These quantum fluctuations are particularly significant for our discussion of cosmic centrality. They represent tiny random variations in density that were present in the earliest moments of the universe's existence. During inflation, these microscopic quantum fluctuations were stretched to macroscopic scales, becoming the seeds of all cosmic structure. The fact that these fluctuations were random and distributed uniformly across space reinforces the idea that the universe didn't expand from a special central point. It expanded uniformly from an initially homogeneous state, with random variations that were the same everywhere on average. If the universe had a center, we would expect the pattern of these fluctuations to show some systematic variation with distance or direction from that center. But what we observe is a random pattern with no preferred orientation or location. The statistical properties of these fluctuations, their power spectrum, and higher-order correlations match exactly what we would expect from a universe that expanded uniformly, with no special central point. The CMB also allows us to test for more subtle forms of cosmic asymmetry. Some theories propose that the universe might have a preferred direction or axis concept, sometimes called cosmic anisotropy. Such theories predict specific patterns in the CMB that would reveal this special direction, but despite careful searches, no convincing evidence for such a pattern has been found. The CMB remains remarkably isotropic once we account for our own motion and the small random fluctuations. The motion correction I mentioned is itself interesting. Our solar system is moving relative to the rest frame of the CMB at about 371 kilometers per second. This motion creates a Doppler effect. The CMB appears slightly hotter in the direction we're moving, where the wavelengths are compressed, and slightly cooler in the opposite direction, where the wavelengths are potreat. Stretched. This pattern is clearly visible in raw CMB maps, creating a distinctive dipole pattern across the sky. But this pattern doesn't reflect a feature of the universe itself, it's simply a result of our own motion. When cosmologists analyze the CMB, they first subtract this dipole pattern to see the intrinsic variations in the background radiation. Once this correction is applied, the CMB shows no preferred direction. This reinforces the point that there's no absolute rest frame in the Universino special reference point that could be considered the center from which everything moves. The CMB also gives us insight into the overall geometry of space. By analyzing the size of the temperature fluctuation specifically, the angular scale of what cosmologists call the first acoustic peak in the CMB power spectrum, we can determine whether space is flat, positively curved, or negatively curved. These measurements indicate that space is flat within about a 0.4% margin of error. This flatness has important implications for the question of cosmic centrality. In a flat universe that extends indefinitely, there simply cannot be a geometric center. Every point is surrounded by infinite space in all directions. No location is special or privileged in terms of its position relative to the whole. The flatness of space, as revealed by the CMB, thus provides further evidence against the notion of a cosmic center. Some people wonder whether the CMB itself might define a special frame of reference, a universal rest frame, against which all motion could be measured. In a sense, it does provide such a reference frame. We can define a CMB rest frame as one in which the background radiation appears the same in all directions, with no dipole pattern. But this doesn't imply a central point in space. An observer anywhere in the universe could determine their motion relative to the CMB and define the same rest frame. This reference frame is associated with the universe's expansion, not with a special central location. The CMB not only shows us the state of the universe at the time of recombination, about 380 years after the Big Bang, but also gives us indirect information about even earlier epochs. The patterns we observe in the temperature fluctuations were established during inflation, just a tiny fraction of a second after the beginning. These patterns were then preserved in the distribution of matter and radiation, eventually becoming visible to us when the universe became transparent. This means the CMB provides our earliest direct observational window into cosmic history, and what it shows us is a universe that was remarkably uniform, with only tiny random fluctuations that were statistically the same everywhere. This uniformity strongly supports the idea that the Big Bang happened everywhere simultaneously, not at a single point from which everything expanded. As we map the CMB with increasing precision, we're able to extract more and more information about the early universe. Beyond the temperature fluctuations, we can measure the polarization of the background radiation, the preferred orientation of the electromagnetic waves. This polarization provides additional details about the physics of the early universe, including the process of reionization, when the first stars formed, and their radiation ionized the neutral hydrogen in the universe, and potentially even the gravitational waves produced during inflation. These increasingly detailed observations continue to support the standard cosmological model, which includes the principle that the universe has no center. The CMB shows us a cosmos that began in a hot, dense state that was nearly uniform everywhere, with small random fluctuations that were statistically identical in all regions. This picture is incompatible with the idea of a central point from which everything expanded. As you drift toward deeper sleep, visualize the CMB as it appears in all-sky Mapsa, nearly uniform glow with tiny random variations in temperature, covering the entire celestial sphere. These variations, represented in false color as slightly warmer and cooler regions, show no pattern that would indicate a preferred direction or central point. They are simply random fluctuations, statistically the same everywhere, that became the seeds of all cosmic structure. This ancient light has been traveling through space for 13.8 billion years, stretched by cosmic expansion from visible light to microwave radiation. It carries information about the earliest accessible moments of cosmic history, telling us that the universe was remarkably uniform from the beginning, with no special central point from which everything expanded. The CMB is, in a sense, the oldest photograph of the universe, a snapshot from when it was just 380 years old. And what this photograph shows us is a cosmos without a center, expanding uniformly in all directions, with the same physical conditions everywhere on average. It confirms what theory suggests. The universe didn't begin from a point in pre-existing space, but expanded everywhere simultaneously, with every region experiencing the same cosmic evolution. To truly understand why the universe has no center, we must grapple with what the CMB reveals: a cosmos that was born nearly uniform, expanded uniformly, and continues to evolve according to the same physical laws throughout its vast, possibly infinite expanse. The symmetry of the background radiation tells us that no location is cosmically special, no direction is preferred, no point can claim to be the center from which everything emerged. In the darkness behind your closed eyelids, imagine this ancient light now invisible to human eyes, but detectable by sensitive radio telescopes, bathing Earth from all directions. It comes not from a special region of space that could be called the center of the universe, but from everywhere, from the entire cosmic horizon, in all directions. And it tells us the same story, no matter which way we look. The universe began everywhere at once, expanded uniformly, and has no special central point. The CMB represents one of science's most remarkable discoveries: direct observational evidence of the Big Bang, confirmation of the expanding universe model, and proof that the cosmos was born in a hot, dense state that was nearly uniform everywhere. Its discovery changed our understanding of cosmic history forever and earned Penzias and Wilson the Nobel Prize in Physics. And one of its most profound implications is that the universe truly has no center, a conclusion supported by its extraordinary symmetry across the entire sky. As your consciousness ebbs toward the shores of sleep, rest in the knowledge that the oldest light in the universe confirms what we've discussed throughout this journey. The cosmos didn't expand from a central point, but expanded everywhere simultaneously. The Big Bang wasn't an explosion in space, but the beginning of space itself, everywhere at once. And the universe continues to expand not from a hub but throughout its entire vast expanse. The ancient light of the CMB, reaching us from all directions after a journey of 13.8 billion years, tells us this story with remarkable clarity and precision. Tomorrow, we'll explore how computer simulations help us visualize and understand a universe without a center. We'll see how these virtual cosmic laboratories confirm that observers anywhere would see the same pattern of expansion that we do. But for now, let the symmetry of the cosmic microwave background guide your thoughts toward peaceful rest. In a universe without a center, every location participates equally in the cosmic expansion. Every region experiences the same physical laws. Every point is surrounded by the same ancient light, arriving from all directions with the same message. The universe has no center, and your place in it is neither central nor peripheral, but simply your unique vantage point on the vast, expanding cosmos. Astronomers and cosmologists have powerful tools beyond direct observation to help us understand the universe's structures. Supercomputer simulations that model cosmic evolution from the earliest moments after the Big Bang to the present day. These virtual universes serve as cosmic laboratories where scientists can test theories, explore hypothetical scenarios, and visualize processes that unfold over billions of years. When it comes to understanding why the universe has no center, these simulations provide particularly compelling evidence. Modern cosmological simulations typically begin with conditions matching what we know about the early universe from observations of the cosmic microwave background radiation. They start with a nearly uniform distribution of matter, with tiny random fluctuations, a computational representation of the universe, shortly after the Big Bang. The simulation then applies the known laws of physics, particularly gravity and fluid dynamics, and evolves this initial state forward in time, showing how structure forms and the cosmos expands. What's remarkable about these simulations is that they reproduce the observed large-scale structure of the actual universe with striking accuracy. When we compare the distribution of galaxies and clusters in these virtual universes with what we observe through our telescopes, we find the same web-like pattern, filaments and walls of galaxies surrounding vast cosmic voids. This success gives us confidence that the underlying physics and initial conditions used in the simulations accurately represent reality. But for our discussion of cosmic centrality, the most important aspect of these simulations is what they reveal about perspective. From any vantage point in the simulation, an observer would see galaxies receding in all directions, with speeds proportional to their distances. Every location experiences the universe expanding around it. None sits at a special central point from which everything moves away. This fundamental insight that the view from anywhere would be essentially the same as the view from here represents one of the most powerful confirmations that the universe truly lacks a center. The simulations allow us to adopt a perspective that would be physically impossible for us to achieve, to place ourselves at distant points in the cosmos and see what an observer there would experience. If the universe had a true center from which everything expanded, then the view from different locations would show systematic differences. Observers closer to this hypothetical center would see galaxies receding in a different pattern than observers far from it, but the simulations show no such variation. An observer in a virtual galaxy billions of light years from our location would see the same basic pattern of cosmic expansion that we do all distant galaxies moving away, with speed proportional to distance. These simulations don't merely suggest this conclusion, they demonstrate it visually and quantitatively. Scientists can place virtual observers at any point in their simulated cosmos and render the view from that location. They can generate artificial sky surveys, mock catalogs of galaxies, and simulated maps of cosmic expansion as seen from anywhere. And consistently, these different perspectives show the same fundamental pattern. Cosmic expansion appears centered on the observer, regardless of where that observer is placed. This uniformity of perspective from any vantage point is only possible if space itself is expanding. Cosmic expansion is not an explosion from a central point, but a stretching of the fabric of the universe that happens everywhere, simultaneously. The simulations thus provide a powerful visualization of why the universe has no center. Beyond confirming the absence of a cosmic center, these simulations help us understand how structure forms in an expanding universe. They show how the tiny fluctuations in the early universe, the small variations in density visible in the cosmic microwave background, grow over time through gravitational attraction. Slightly denser regions attract more matter, becoming progressively denser, while less dense regions become more empty. This process leads to the cosmic web structure we observe today, network of galaxy clusters and superclusters separated by vast voids. What's striking about this structure formation is that it happens the same way throughout the simulated universe. There's no special region where galaxies form earlier or in greater abundance. The statistical properties of the cosmic web, the sizes of voids, the distribution of filaments, the clustering of galaxies are the same everywhere, once you look at sufficiently large scales. This uniformity further confirms the absence of a cosmic center. The largest and most sophisticated of these simulations, such as the Millennium Simulation, the Illustris Project, or the Eagle Simulation, track the evolution of billions of particles representing dark matter, gas, stars, and even supermassive black holes. They incorporate not just gravity, but also the complex physics of gas dynamics, star formation, and the feedback effects of supernovae and active galactic nuclei. This allows them to reproduce not just the large-scale distribution of galaxies, but also their internal structures and properties. These simulations require enormous computational resources, supercomputers, with thousands of processors running for months. The Millennium Simulation, for example, tracked over 10 billion particles representing the distribution of matter in a cubic region of space, about 2 billion light-years on each side. More recent simulations like Illustris TNG follow even more particles with more sophisticated physics models. What makes these simulations particularly valuable is that they allow us to watch cosmic evolution unfold, something we cannot do through direct observation. We can only see the universe as it is now, or rather, as it was when the light we're currently receiving left its source. We can't observe how a particular galaxy or cluster formed and evolved. But in simulations, we can track the entire history of any structure, from the tiny seed fluctuations in the early universe to the complex galaxies and clusters of the present day. This historical perspective reveals that the universe evolved in essentially the same way everywhere. While the specific configuration of galaxies and clusters varies from region to region, each part of the cosmic web has its unique arrangement. Just as each snowflake has its unique pattern, the statistical properties and evolutionary pathways are the same throughout. There is no special region that evolved differently or that could be identified as the center of cosmic evolution. The simulations also allow us to extrapolate into the future, showing how cosmic expansion will continue to unfold. They confirm that the accelerating expansion driven by dark energy will eventually isolate galaxies from one another. Clusters that aren't gravitationally bound will recede beyond their mutual cosmic horizons, becoming permanently invisible to each other. But this process happens the same way throughout the universe. There's no special central region that remains connected while others separate. One of the most powerful aspects of these simulations is their ability to test alternative cosmological models. Scientists can adjust the parameters of the simulation, changing the amount of dark matter, dark energy, or ordinary matter, modifying the expansion rate, altering the initial conditions, and see how these changes affect cosmic evolution. They can even test entirely different physical laws, or add exotic components like cosmic strings or domain walls. These alternative simulations consistently show that a universe with a center would look very different from what we observe. If cosmic expansion proceeded from a central point rather than happening uniformly throughout space, galaxies would show systematic patterns in their velocities and distributions. There would be a gradient in the ages and properties of galaxies, with those closer to the center having formed earlier. The cosmic microwave background would show a distinctive pattern pointing toward or away from this center. None of these signatures of centrality appear in our observations of the actual universe, and simulations based on a centerless, uniformly expanding cosmos match what we see with remarkable accuracy. This consistency between theory, simulation, and observation gives us high confidence that the universe truly lacks a center. But perhaps the most philosophically significant aspect of these simulations is how they help us transcend the limitations of our perspective. As physical beings located at a specific point in space and time, we can only directly observe the universe from one vantage point alone. But our minds, aided by mathematics and computation, can transcend this limitation. Through simulation, we can adopt a kind of cosmic perspectiva view from everywhere and nowhere, seeing the universe not just as it appears to us, but as it would appear from any location. This liberation from the constraints of our specific cosmic address represents one of science's most profound achievements. Throughout history, humans have unconsciously projected the biases of their perspective onto the cosmos, assuming that what we see from our vantage point reflects some absolute truth about the universe. We assumed Earth was at the center because that's how the sky appeared to move from our perspective. We assumed the Milky Way was the entire universe because that's all we could see before developing powerful enough telescopes. Modern cosmology, especially as embodied in these simulations, frees us from these perspectival biases. It shows us that our view of the universe is just one among countless possible viewpoints, none more central or privileged than any other. The motion of galaxies away from us doesn't indicate that we're at a special point, any more than a passenger on a train seeing the landscape move past indicates that the train is stationary and the world is moving. In these simulations, we can see visually and immediately what would otherwise require abstract mathematical reasoning to grasp that cosmic expansion would look the same from any galaxy. We can watch as virtual observers placed at different locations in the simulation all reach the same conclusion. Everything seems to be moving away from them. We can see directly that this apparent centrality is an illusion of perspective, not a physical reality. The simulations also help us grasp another counterintuitive aspect of a centerless universe, that it doesn't need to expand into anything. Many people, when first encountering the concept of cosmic expansion, naturally ask, what is the universe expanding into? This question assumes that the universe is a bounded object within some larger space, like a balloon inflating in a room. But the simulations show how space itself can expand without requiring any external container. In these virtual universes, the boundary conditions are typically periodic, meaning that if you travel far enough in one direction, you would return to your starting point from the opposite direction, like in some video games, where exiting the right edge of the screen brings you back in from the left. This creates a finite volume that has no edge or boundary, but can still expand as the coordinates themselves stretch. While we don't know if our actual universe has such periodic boundary conditions, this computational approach demonstrates how expansion doesn't require an external something to expand into. Another valuable insight from cosmological simulations concerns the observable universe. Every observer, regardless of location, sees their own spherical observable universe, the region from which light has had time to reach them since the Big Bang. In simulations, we can visualize these different observable spheres and see how they overlap. We can understand visually why every observer is at the center of their observable universe, not because any location is cosmically special, but simply because that's how observation works given the finite speed of light and the finite age of the universe. Perhaps most importantly, these simulations help us appreciate the true nature of the Big Bang. By tracking the evolution of the universe backward as well as forward, they show that the beginning wasn't an explosion at a point, but a condition that encompassed all of space. When the simulation reaches its earliest moments, we don't see matter converging to a central location. Instead, we see all of space in a hot, dense state, with every region compressed equally. This visualization helps dispel the persistent misconception that the Big Bang was like a conventional explosion from a central point. The most advanced simulations now incorporate not just the formation of galaxies and large-scale structure, but also the evolution of individual solar systems, the birth and death of stars, the synthesis of chemical elements, and even the potential for habitable planets. They show that these processes occur throughout the universe according to the same physical laws, with no special region where life or complexity is more likely to emerge. The conditions that allowed our existence here in the Milky Way are replicated countless times throughout the simulated cosmos, further undermining any claim to cosmic centrality or specialness based on our location. As supercomputing power continues to increase, these simulations become ever more detailed and comprehensive. The next generation of cosmological simulations will track trillions of particles over even larger volumes of space, with more sophisticated models of the physics involved. They will provide even more detailed virtual views from different cosmic locations, further confirming the fundamental symmetry of perspective that characterizes a universe without a center. As you drift toward deeper sleep, imagine what these simulations reveal: vast volumes of virtual space where galaxies form, clusters assemble, and cosmic structure emerges in a dance of gravity and expansion. Picture yourself as a virtual observer, placed at different locations throughout this simulated cosmos. From each vantage point, you would see galaxies receding in all directions. From each perspective, the universe would appear to be expanding around you, yet none of these locations is truly central. Each simply provides its own window on the same cosmic process. This equality of perspective isn't just a scientific fact, it's a philosophical insight with profound implications. It teaches us that significance doesn't come from occupying a geometrically central position. It comes from awareness, from the capacity to observe and comprehend the cosmos, regardless of where one is located within it. In a universe without a center, meaning isn't assigned by placement, but created through consciousness and understanding. The simulations confirm what theory suggests and observation indicates. The universe expands uniformly, with no special central point. Every location experiences cosmic evolution according to the same physical laws. Every observer sees the same basic pattern of expansion. This fundamental democracy of perspective is one of the most profound insights of modern cosmology, and these virtual universes make it visually and intuitively accessible. Tomorrow, we'll explore the philosophical implications of living in a centerless universe, how this cosmological fact challenges traditional notions of human significance and invites us to find meaning not in special placement but in consciousness and connection. But for now, let the insights from these cosmic simulations guide your thoughts toward peaceful rest. In the virtual laboratories of computational cosmology, the evidence is clear. The universe has no center, and every perspective is equally valid, equally true, and equally part of the vast cosmic whole. As your consciousness ebbs toward the shores of sleep, imagine exploring these simulated universes flying through virtual space, witnessing the formation of galaxies, and experiencing cosmic expansion from countless different vantage points. In each location, the view is different in its details, but the same in its essence. In each place, the cosmos unfolds according to the same physical principles. In each perspective, the universe appears to expand outward in all directions. And in that symmetry of experience lies one of the most profound truths of modern cosmology. The universe has no center, and every viewpoint is simply one window on the same vast, expanding reality. The absence of a cosmic center extends far beyond astronomy and physics. It reverberates through our philosophical understanding of existence itself. Throughout human history, our cosmological models have profoundly shaped how we view our place in the universe and the meaning we ascribe to our lives. The discovery that the universe has no center represents not just a scientific revolution, but a philosophical one with deep implications for how we understand ourselves and our significance. In ancient cosmologies across many cultures, humans were placed at the center of creation. The Greek astronomer Ptolemy formalized this view in his geocentric model, where Earth stood fixed at the middle of the cosmos, with celestial bodies revolving around it in perfect circles. This wasn't merely a scientific theory, but a philosophical statement about humanity's importance. Being at the center implied specialness, purpose, and design. Medieval European thought integrated this geocentric view with Christian theology, creating a cosmos where Earth, and by extension, humanity occupied the central position in God's creation. The physical center of the universe aligned with the spiritual center of divine attention. Earth's central placement reflected humanity's central role in the cosmic drama of creation, fall, and redemption. When Copernicus proposed his heliocentric model in the 16th century, moving Earth from the center to just one planet orbiting the Sun, the implications extended far beyond astronomy. It initiated what historians call the Copernican Revolution, a profound shift in how humans understood their place in the cosmos. No longer at the physical center, humanity's special status was called into question. As Freud later noted, this represented one of the great wounds to human narcissism, the realization that we do not occupy a privileged position in the physical universe. This decentering process has continued through modern cosmology. As telescopes improved, we realized our Sun is just one star among billions in the Milky Way, located in an unremarkable region far from the galactic center. Then we discovered our galaxy is just one among billions more, again with no special central position in the cosmos. Now we understand that the universe itself has no center or final, and complete decentering that removes any claim to cosmic specialness based on location. This progression represents what philosopher Hans Blumenberg called the Copernican turn in significance, a shift from finding meaning through central position to finding meaning through other means. If humans aren't at the center of creation physically, we must reconsider what gives our existence value and purpose. Does significance require centrality, or can it be found elsewhere? This question has occupied philosophers and theologians for centuries. Blaise Pascal, writing in the 17th century after the Copernican Revolution, but before the full extent of cosmic vastness was understood, captured the existential vertigo induced by this decentering. The eternal silence of these infinite spaces frightens me. For Pascal, the vastness of the cosmos and humanity's non-central position within it created a spiritual crisis. Where is God in such a universe? What significance can human life have when situated in such an indifferent expanse? Yet Pascal found a resolution through an inward turn, suggesting that human significance lies not in our physical centrality, but in our capacity for consciousness and self-reflection. Man is but a reed, the weakest in nature, but he is a thinking reed, Pascal wrote. Our dignity comes not from our position in space, but from our ability to comprehend the universe that contains us. We may occupy no special cosmic location, but we possess the remarkable ability to understand this facto, grasp our own non-centrality. This philosophical move, finding significance in consciousness rather than location, has become increasingly important as our understanding of the universe's scale and structure has developed. In a cosmos without a center, where no position is geometrically privileged, meaning cannot be derived from placement, it must come from other sources. Some philosophical traditions have embraced this decentering as liberating rather than threatening. Existentialist thinkers like Jean-Paul Sartre and Albert Camus suggested that the absence of a predetermined cosmic order, including the absence of a central place for humanity, frees us to create our own meaning. If the universe doesn't place us at its center, it also doesn't dictate our purpose. We are responsible for defining our own significance. Similarly, some Buddhist perspectives have long emphasized the absence of a fixed self or central point of reference. The concept of no self, anatta, and the interconnectedness of all phenomena align in interesting ways with a cosmic model that lacks a center. Just as the universe expands uniformly with no privileged location, so too does existence unfold without requiring a central, permanent self. The philosophical implications of a centerless universe extend to questions of cosmic purpose. In traditional religious cosmologies, where Earth occupied the center of creation, it was easier to imagine that the entire cosmos was designed with humanity in mind. The sun existed to provide light and warmth for us. The stars were placed in the heavens for our benefit and contemplation. But in a universe of 2 trillion galaxies, where our planet orbits one ordinary star among billions in one galaxy among billions more, this anthropocentric view becomes difficult to maintain. Yet this need not lead to nihilism or a sense of meaninglessness. Many philosophers and scientists have suggested that significance doesn't require centrality or even purpose. The astronomer Carl Sagan expressed this perspective eloquently. We are the local embodiment of a cosmos grown to self-awareness. We have begun to contemplate our origins, star stuff, pondering the stars. Organized assemblages of 10 billion atoms, considering the evolution of atoms. tracing the long journey by which, here at least, consciousness arose. In Sagan's view, our significance lies not in occupying a special position, but in our capacity to comprehend the cosmos that produced us. We are the means by which the universe has become conscious of itself. This perspective finds wonder not in being at the center, but in being connected to everything made of the same elements forged in ancient stars, subject to the same physical laws that govern distant galaxies. Philosopher Thomas Nagel has considered whether human significance might lie in our capacity to adopt what he calls the view from nowhere, a perspective that transcends our particular situation and grasps objective reality. Science, particularly cosmology, represents an effort to achieve this perspective, understanding the universe not just as it appears to us from our limited vantage point, but as it actually is. The discovery that the universe has no center is itself a triumph of this objective viewpoint. We've transcended the bias of our particular perspective to grasp a deeper truth. The absence of a cosmic center also has implications for how we think about equality and hierarchy. Throughout history, cosmological models with centers have often been used to justify social and political hierarchies. The great chain of being in medieval thought placed God at the top, followed by angels, humans, animals, plants, and minerals in descending order of importance. This vertical cosmic model, with Earth at the center of concentric celestial spheres, mirrored and justified hierarchical social structureskings at the center, nobles around them, and commoners at the periphery. A centerless universe undermines this hierarchical model. If no location in space is privileged, if every point is on equal geometric footing, then cosmic structure itself no longer provides a template for social hierarchy. We might instead find in the uniform expansion of the universe a model for equal at each location, experiences the same cosmic evolution, subject to the same physical laws, equally part of the whole. The philosopher Hannah Arendt saw profound political implications in the Copernican revolution and subsequent cosmological discoveries. For Arendt, the modern age began not with philosophical or political developments, but with the telescope Peace instrument that allowed humans to adopt a perspective beyond Earth and recognize our non-central position. This shift required us to reconsider the basis of authority and legitimacy in human affairs, as the cosmic order could no longer be invoked to justify earthly hierarchies. Even our conception of God has been influenced by cosmological understanding. Traditional Western theology often located God above the world, at the top of a vertical cosmic hierarchy. But in a universe with no absolute up or down, no center, and no edge, such spatial metaphors become problematic. Theologians like Paul Tillich have responded by reconceiving God not as a being located somewhere, but as the ground of being itself, present throughout reality, rather than situated at a particular cosmic location. Process theology, associated with philosophers like Alfred North Whitehead and Charles Hartshorne, similarly reconceives God's relation to the universe in non-centralized terms. Rather than viewing God as a monarch ruling from a central throne, process thought sees divine activity as distributed throughout the cosmos, involved in every location equally, privileging none but engaged with all. The absence of a cosmic center also challenges how we think about time and history. In many traditional cosmologies, time had a central moment creation from which history unfolded in a linear progression. This temporal centrality mirrored spatial centrality, with certain moments regarded as more significant than others because of their proximity to the beginning. Modern cosmology suggests a different temporal structure. While the Big Bang represents a beginning point for our observable universe, it wasn't a special moment at a special location, but an event that encompassed all of space. And if the universe is infinite, even this temporal centrality becomes questionablean. Infinite cosmos might not have an absolute beginning, or might include regions with different histories and timelines. This temporal decentering parallels the spatial decentering we've explored. Just as no location is cosmically special, perhaps no moment is absolutely central to the cosmic story. Each instant, like each position, simply is what its own point in a vast continuum, neither elevated nor diminished by its relation to a hypothetical center. Yet this seeming demotion, this removal from the center of both space and time, can actually enhance our appreciation for the remarkable fact of consciousness. In a universe with no privileged locations, the emergence of beings capable of contemplating their own existence and the cosmos that contains them stands out as truly extraordinary. The physicist Freeman Dyson captured this perspective. As we look out into the universe and identify the many accidents of physics and astronomy that have worked together to our benefit, it almost seems as if the universe must in some sense have known we were coming. Not because we occupy a special central location, but because the universe's evolution has produced the capacity for self-reflection and understanding. As you drift closer towards sleep, consider how the absence of a cosmic center might liberate rather than diminish us. We need not claim a special position to claim meaning. We need not stand at the center to stand in wonder. Our significance derives not from where we are, but from what we are, conscious entities capable of comprehending a universe that extends without limit in all directions, with no preferred center. This shift from central placement to conscious awareness as the source of significance parallels other philosophical developments in the modern age. It aligns with existentialist emphasis on existence preceding essentia, lack of a predetermined place or purpose, freeing us to create meaning. It resonates with phenomenological attention to consciousness and experience as primary philosophical concerns. It connects with environmental ethics that recognize humanity not as the center of nature but as one strand in the web of life. In a universe without a center, significance becomes less about position and more about perception, less about location and more about awareness, less about being in the right place and more about seeing clearly wherever we happen to be. We are not important because we stand at the center. We are important because we can understand that there is no center and find meaning in that very understanding. This philosophical perspective invites a certain cosmic humility. We are not the focal point of creation, not the physical center around which everything revolves, but it also invites a cosmic dignity. In a universe of profound symmetry, where no location is privileged over any other, our consciousness represents an extraordinary developmental capacity for wonder, understanding, and meaning-making that transcends our particular cosmic address. Perhaps most profoundly, a centerless universe invites us to find connection rather than centrality. If no point is special because of its location, then all points are connected through their equal participation in the cosmic whole. We may not be at the center of everything, but we are part of everything made of elements forged in ancient stars, governed by the same physical laws that operate in distant galaxies, participating in the same cosmic expansion that characterizes the universe everywhere. This connectedness offers a different kind of significance than central placement. It suggests that meaning emerges not from hierarchy but from relationship, not from being above or below or at the middle, but from being integrated into the vast, expanding cosmic community, related to everything else through shared origin and shared physical laws. As consciousness fades and sleep approaches, let this philosophical perspective gently reshape how you think about your place in the cosmos. You are not at the center of everything, but you are not meant to be. Significance doesn't require centrality. Meaning doesn't depend on special placement. In a universe that expands uniformly in all directions, with no preferred center, your significance comes not from where you are, but from your capacity to wonder, to understand, to connect. The universe hasn't placed you at its center, but it has produced in you the remarkable ability to comprehend this very facto, grasp the vastness and symmetry of a cosmos that expands without preference for any location. And in that consciousness, that capacity for understanding, lies a significance that transcends any geometric centrality, any special cosmic address. Rest now in that awareness, drifting toward dreams in a universe that extends without limit in all directions, with no center to seek, no special place to find, just the vast, expanding fabric of space and time in which your consciousness flickers like a star, unique, not because of where it shines, but because it shines at all. As our exploration of the centerless universe continues, we encounter an intriguing question that pushes at the boundaries of modern cosmology. Could there exist a larger realitia, multiverse containing many universes? And might such a structure have a center? This question takes us from established science into more speculative territory, where theoretical physics meets philosophy and where our understanding reaches its current limits. The concept of a multiverse has emerged from several different threads in contemporary physics. Inflationary theory, which describes an extremely rapid expansion in the earliest moments after the Big Bang, suggests that our observable universe might be just one bubble in an eternally inflating cosmos. String theory, which attempts to unify quantum mechanics and general relativity, proposes the existence of a vast landscape of possible universes with different physical laws and constants. Quantum mechanics itself, particularly in the many worlds interpretation, suggests that reality continually branches into multiple universes where different possible outcomes occur. These various multiverse theories differ in their details, but they share a common implication. Our universe, vast as it is, might be just one region or component of a much larger structure. And this raises the question, could this larger structure have a center, even if our particular universe does not? In the inflationary multiverse scenario, our universe began as a bubble of space that stopped inflating, while the surrounding space continued to expand at an accelerating rate. This created what physicists call a pocket universe, a region with its own laws of physics and its own history, separated from other such bubbles by rapidly inflating space. In this model, new bubble universes are continually forming in the inflating space between existing bubbles. This process has been compared to the formation of bubbles in boiling water or the appearance of bubbles in rising bread dough. Just as these physical processes don't create bubbles around a special central point, but generate them wherever conditions are right, inflationary theory suggests bubble universes form throughout the inflating multiverse, without preference for any particular location. However, inflation had to start somewhere and some when. If the entire multiverse began from a single initiation of inflazione, first moment when exponential expansion began, then one could argue that this starting point represents a kind of center for the multiverse. Not a geometric center within space, but a central event from which everything else evolved. But even this temporal center becomes questionable in some versions of inflationary theory. If inflation is eternal, if it has always been occurring and will always continue, then there is no first moment and thus no temporal center. The multiverse simply exists, eternally producing new bubble universes without beginning or end. String theory proposes a different kind of multiversione, consisting of numerous universes with different physical laws, constants, and dimensions. These universes aren't spatially connected in the conventional sense. They represent different possible configurations of the fundamental building blocks of reality. In this landscape of possible universes, ours is just one where the physical constants happen to allow for the formation of stars, planets, and life. Could this landscape of possible universes have a center? Not in the geometric sense we've been discussing. These universes aren't arranged in space like objects on a table or bubbles in foam. They exist in a more abstract space of possibilities, where distance isn't measured in meters or light years, but in terms of how different the physical laws are from one universe to another. One could imagine a kind of central universe in this landscape, perhaps one with the simplest physical laws or the most symmetrical structure. But this would be a mathematical or conceptual centrality, not a geometric one. It wouldn't imply that this universe is physically at the middle of anything, or that others are distributed around it in space. The many worlds interpretation of quantum mechanics suggests yet another kind of multiversone, where reality continually branches into multiple versions, with each possible outcome of a quantum event realized in some branch of the universal wave function. In this model, there are countless versions of our universe where history took slightly different paths due to different quantum outcomes. This quantum multiverse doesn't have a center in any meaningful sense. There's no special branch from which all others emerge. The branching occurs everywhere continuously. While our particular branch of reality has its own history and evolution, it doesn't occupy a privileged position in the overall structure of the quantum multiverse. So, while various multiverse theories propose different ways in which our universe might be part of a larger structure, none of them clearly establishes a central point or location. The multiverse, like our universe, appears to lack a geometric center. But even if the multiverse exists and lacks a center, our universe still behaves as if it has no center. The bubble that holds us expands evenly, and we cannot see beyond it. In this sense, center remains a relative term. Even within a multiverse, every universe might expand from its own field, lacking a central point. And we, inside ours, would still float without privilege. This is an important point. Regardless of whether our universe is all that exists, or just one component of a larger multiverse, the observable evidence indicates that our cosmos has no center. Galaxies recede from us in all directions at speeds proportional to their distances. The cosmic microwave background radiation is remarkably uniform across the sky. Computer simulations show that observers anywhere would see the same pattern of expansion. These observations remain true whether our universe stands alone or is embedded in a larger structure. The concept of a multiverse raises profound philosophical questions about uniqueness and typicality. If our universe is just one among many, perhaps infinitely many, then nothing about it is absolutely unique. There may be other universes identical to ours, or nearly so. There may be versions where history took slightly different paths, where different civilizations arose, where different individuals contemplate these same questions. This possibility challenges our sense of cosmic uniqueness. If there are multiple versions of Earth, multiple versions of you reading these words, or slight variations of them, multiple versions of every moment and every choice, then what becomes of individuality and significance? Does the potential infinity of the multiverse render everything mundane through endless repetition? Some philosophers argue the opposite, that the multiverse enhances rather than diminishes significance. If our particular universe, with its specific constants and conditions that allow life to emerge, is just one possibility among countless others, where different laws of physics prevail, then the fact that we exist at all becomes remarkable. Our universe isn't the only possible one. It's just one where the conditions happen to be right for complexity and consciousness to develop. This perspective aligns with what physicists call the anthropic principle, the idea that we shouldn't be surprised to find ourselves in a universe whose properties allow for our existence, regardless of how unusual such a universe might be in the larger multiverse. If most possible universes are sterile and lifeless due to different physical constants, then conscious observers will only ever find themselves in the rare universes where conditions permit their existence. The anthropic principle doesn't require our universe to be at the center of anything. It simply recognizes that observers can only exist in universes compatible with their existence, a seemingly circular but profound insight that helps explain why our universe seems so finely tuned for life without requiring it to be specially designed or centrally positioned. Even if there is a multiverse, we can only directly observe and study our own universe. The boundaries of our observation are set by the cosmic horizon, the distance beyond which light has not had time to reach us since the Big Bang. This horizon surrounds us in all directions, creating the spherical observable universe with Earth at its center. But as we've discussed, this apparent centrality is merely a consequence of our location and the finite speed of light, not a sign of cosmic significance. If other universes exist beyond our cosmic horizon, or in other dimensions or branches of reality, they remain empirically inaccessible to us, at least with current methods. We can theorize about their existence based on mathematics and inference, but we cannot directly observe them. This empirical barrier has led some philosophers of science to question whether multiverse theories should be considered scientific at all, since they appear to make predictions that cannot be tested. However, multiverse theories might leave indirect evidence within our observable universe. For instance, if our universe collided with another bubble universe in the distant past, this might leave a detectable pattern in the cosmic microwave background radiation. Or if our universe is one of many that branched off during eternal inflation, the mathematics of that process might predict certain observable features of our cosmic structure. Scientists continue to search for such evidence, which would provide empirical support for multiverse theories. But even if such evidence were found, if we confirm that our universe is one bubble in a vast cosmic foam, or one branch in an endlessly dividing quantum tree, we would still face the question of whether this larger structure has a center. And current theoretical models suggest it does not, at least not in the geometric sense we've been discussing. This consistency, the absence of a center at all levels of cosmic structure, suggests a profound symmetry in reality. From the distribution of galaxies within our observable universe to the theoretical arrangement of universes within a potential multiverse, we find no evidence for a central hub or privileged location. Everywhere we look, from the smallest scales to the largest, we find systems that lack geometric centrality. This pattern aligns with a fundamental principle in modern physics, the homogeneity and isotropy of space. These properties, which state that space is the same everywhere, homogeneity, and looks the same in all directions, isotropy, are built into the foundation of general relativity and cosmology. They reflect a deep symmetry in the physical laws that govern our universe and, potentially, any larger structure in which it might be embedded. Some philosophers see in this symmetry a kind of cosmic democracy, a universe, or multiverse, that doesn't privilege any location over any other. No point can claim to be the center. No position confers special status. Each location, each universe, each perspective exists on equal footing with all others. This democratic cosmos stands in stark contrast to ancient and medieval models, which placed Earth at the center of concentric celestial spheres, with heaven above and hell below, creating a vertical hierarchy of spiritual significance aligned with spatial position. In the modern cosmological view, no location is inherently higher or lower, more central or more peripheral than any other. Yet within this geometric equality, remarkable differences emerge. Some regions of space contain galaxies, others are vast voids. Some planets harbor life, others are barren. Some locations give rise to consciousness and contemplation, others remain forever mindless matter and energy. This diversity within symmetry suggests that significance isn't conferred by position, but by process, not by where something is, but by what happens there. If the multiverse exists, this principle would extend to the larger cosmic structure. Some universes might harbor complexity and consciousness, others might remain simple and sterile due to different physical laws. Some might cultivate intelligence capable of contemplating the multiverse itself, others might never develop observers of any kind. This diversity wouldn't reflect central positioning, but rather the particular conditions and evolutionary pathways in each universe. As you drift closer to sleep, consider this possibility, that we live in one bubble universe among perhaps infinitely many, each with its own physical laws and history, none at the center of anything, all equally part of a vast cosmic structure that itself has no center. Our particular bubbler universe expands uniformly in all directions, carrying galaxies along with it, with no special central point. And within this universe, our galaxy, our solar system, our planet occupy no privileged location. Yet here we are, conscious beings capable of contemplating this vast, centerless cosmos. Beings who evolved on a planet with no special cosmic address, but who developed the capacity to understand the very structure of reality. Beings who, for most of history, assumed we must be at the center of everything, only to discover, through careful observation and reasoning, that centrality is an illusion, that the universe, and perhaps the multiverse, expands and evolves without privileging any location. This decentering has been a long, sometimes difficult journey for humanity. We've had to surrender, one by one, our claims to cosmic centrality. We are not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of the universe. And the universe itself may be just one component of a multiverse that also lacks a center. Yet in this journey of decentering, we've gained something profound, a more accurate understanding of our place in the cosmos. We've replaced the comforting illusion of central importance with the awe-inspiring reality of being part of a vast, symmetric, evolving cosmos. We've exchanged the provincial view of a universe centered on us for the grand perspective of a universe, perhaps a multiverse that unfolds according to the same principles everywhere, with no center, no edge, just endless, magnificent complexity. As sleep approaches and consciousness begins to fade, rest in this remarkable truth. You need not be at the center of everything to be significant. You need not occupy a special cosmic location to wonder, to understand, to connect. In a universe without a center, even one that might be part of a multiverse, without a center, your significance comes not from where you are, but from what you are, a conscious participant in the cosmic drama, capable of comprehending the very structure of reality. Tomorrow, we'll explore one final aspect of our centerless cosmos, profound beauty and elegance of a universe that expands uniformly, with no privileged location. We'll see how this symmetry reflects a deep harmony in nature and offers a kind of cosmic peace not found in hierarchical models with centers and peripheries. But for now, drift toward dreams, in the knowledge that the centerless nature of reality doesn't diminish your importance. It simply invites you to find significance beyond location, in consciousness, connection, and wonder. The multiverse, if it exists, doesn't place our universe at its center. Our universe doesn't place our galaxy at its center. Our galaxy doesn't place our solar system at its center. Our solar system doesn't place Earth at its center. And Earth doesn't place any particular location at its center. At each level of cosmic structure, centrality dissolves into symmetric expansion and evolution, with no point more privileged than any other. Yet within this centerless framework, here you are thinking, feeling, wondering, understanding. Your consciousness illuminates a small corner of this vast cosmos like a candle in the night. Not central, not special by location, but remarkable nonetheless for your capacity to comprehend the very absence of centrality, to grasp the symmetric beauty of a universe that expands everywhere at once, with no preferred point. In the silence of the night, as thoughts grow dim and sleep draws near, let go of any lingering attachment to cosmic centrality. Embrace instead the freedom of floating in a centerless cosmosa universe, where your significance depends not on where you are, but on who you are and what you perceive. Not on position, but on awareness. Not on centrality, but on consciousness. And in that understanding, find peace. The universe hasn't placed you at its center, but it has evolved in such a way that you can comprehend its center-free nature. It hasn't made you geometrically special, but it has made you capable of grasping the very concept of specialness and recognizing that it transcends location. In this awareness lies a significance deeper than any central placement could confer, the significance of understanding your place in a cosmos that offers no central place to anyone. There is a special kind of elegance in a universe without a center, a cosmos that doesn't choose sides, that doesn't crown a location, that doesn't elevate one region above others. This centerless model reflects a profound symmetry that permeates nature itself, a harmony of balance, proportion, and motion without hierarchy. In this final chapter of our main journey, we explore the aesthetic and conceptual beauty of a universe that expands uniformly, with no privileged center point. Throughout history, humans have recognized symmetry as a fundamental aesthetic principle. We see it in the bilateral symmetry of the human face and body, in the radial patterns of flowers, in the geometric designs of sacred architecture across cultures. Symmetry represents balance and harmony, qualities we instinctively find pleasing and meaningful. The symmetry of the cosmos's uniform expansion in all directions, with no preferred center, represents a kind of ultimate balance, a perfect equality of all locations. This cosmic symmetry isn't merely beautiful in the abstract sense. It has profound practical implications for how the universe works. The uniformity of cosmic expansion means that the laws of physics operate the same way everywhere. The constants of nature, the strength of gravity, the charge of an electron, the speed of light remain the same throughout the observable universe. Experiments conducted in laboratories on Earth yield the same results as they would if performed in distant galaxies, provided the conditions are equivalent. This consistency of physical law represents one of the most remarkable features of our universe. It means that the cosmos is comprehensible, that we can understand distant regions we'll never visit by applying the same principles we discover here. It means that knowledge gained in one location applies universally. It means that the universe operates according to a coherent set of rules that don't favor any particular place. The beauty of this consistency becomes even more apparent when we consider the alternatives. Imagine a universe where physical laws varied from region to region, where the strength of gravity or the behavior of light depended on proximity to some cosmic center. Such a universe would be chaotic, unpredictable, resistant to unified understanding. The fact that our universe doesn't work this way, that it maintains the same physical principles throughout its vast expanse, represents a deep and beautiful order. This order doesn't require a center. In fact, it's achieved most perfectly through centerlessness, through the complete equivalence of all locations. Every point in the universe experiences the same cosmic evolution, subject to the same physical laws, participating equally in the grand unfolding of space and time. This democracy of position creates a kind of cosmic harmony more profound than any hierarchical arrangement with privileged centers and diminished peripheries. Consider the mathematical elegance of this model. The equations of general relativity that describe cosmic expansion are symmetrical. They work the same way regardless of which location you consider as your reference point. This symmetry isn't just computationally convenient, it reflects a fundamental property of reality. The mathematics doesn't select a special point because the universe itself doesn't have one. The equations mirror the very structure of the cosmos they describe. This mathematical harmony extends to the fundamental forces of nature. The equations describing electromagnetism, the strong and weak nuclear forces, and gravity all possess various symmetries transformations that leave the equations unchanged. These symmetries aren't merely mathematical curiosities, they reveal deep principles about how reality works. And the absence of a cosmic center represents one of the most comprehensive symmetries in nature, what physicists call translational invariance, the principle that the laws of physics don't depend on absolute position. The aesthetic appeal of a centerless universe aligns with what mathematicians and physicists often describe as elegance, the quality of achieving profound results from simple principles. The idea that space expands uniformly in all directions, with no preferred center, represents a remarkably simple concept that explains a vast array of observations: the recession of galaxies, the cosmic microwave background radiation, the distribution of matter on large scales. This parsimony explaining, much with little, exemplifies the elegance scientists seek in their theories. Beyond its scientific and mathematical beauty, the centerless universe offers a kind of philosophical elegance. It presents a cosmos without hierarchy of position, where significance cannot be claimed through central placement. This democratic structure invites us to find meaning not in special location, but in process and awareness, not in being at the center, but in being conscious, regardless of where that consciousness emerges. This shift mirrors what philosophers call the Copernican revolution in thought, the movement from seeing humans as the central focus of creation to recognizing ourselves as participants in a vast cosmic process that doesn't privilege any particular location or perspective. Just as Copernicus showed that Earth isn't at the center of the solar system, modern cosmology shows that no location is at the center of the universe. This decentering doesn't diminish human significance. It recasts it in terms of consciousness and comprehension rather than special placement. The centerless cosmos also offers a certain ethical elegance. Throughout history, claims of central or special position have often been used to justify dominance and exploitation. The belief that Earth was the center of creation sometimes supported the notion that humans had absolute dominion over nature. The idea that certain cultures or nations occupied central positions in the world often reinforced claims of superiority and right to rule. The cosmological insight that no location is central provides a scientific counterpoint to these hierarchical views, a model of reality where position confers no special status or privilege. This doesn't mean the universe enforces equality or dictates ethics. The cosmos operates according to physical laws that are indifferent to human values. But the structure of a centerless universe aligns more naturally with philosophical frameworks that emphasize equality and interconnection rather than hierarchy and domination. It offers a cosmic model that resonates with ethical systems based on the equal inherent value of all beings rather than the superiority of those in central or elevated positions. There is also a temporal beauty in the centerless cosmos. The universe didn't begin at a special central point and expand outward. It began everywhere at once, with each region experiencing the same fundamental evolution. This symmetry in time parallels the symmetry in space. No moment is absolutely central to cosmic history, just as no location is central to cosmic structure. Each instant, like each position, participates equally in the unfolding of reality. This temporal democracy invites us to appreciate the present moment, not because it occupies a special place in cosmic history, but simply because it's where we are, the temporal location from which we experience and observe the universe. The now isn't privileged in any absolute sense, but it's significant to us because it's the moment we inhabit, just as our spatial location is significant to us, not because it's centrally positioned, but because it's where we exist and perceive. As sleep draws nearer and your thoughts grow more diffuse, consider the aesthetic harmony of floating in a centerless cosmos. You are not positioned at the hub of creation, but neither is anyone else. You drift in a universe that expands uniformly in all directions, carrying galaxies, stars, and planets with it. Your location is not central, but it is perfect exactly where you need to be to observe and experience the cosmos from your unique vantage point. This centerless floating brings a certain peace. You need not claim cosmic importance through special placement. You need not justify your significance by reference to a central position. You simply are where you are, own conscious participant in a vast, expanding cosmos that treats all locations with perfect equality. There is freedom in this realization, freedom from the need to be central, freedom to find meaning in awareness rather than position. The elegance of a universe without a middle also offers a kind of cosmic permission to be exactly where you are, permission to find significance without centrality, to permission to matter not because of special placement, but because of special awareness. In a cosmos that doesn't privilege any location, your consciousness becomes remarkable not because of where it emerged, but simply because it emerged at Allah, light of awareness illuminating one small corner of a vast, expanding universe. This perspective invites a certain cosmic humility. You are not at the center of everything, but it also invites a cosmic dignity. In a universe without a middle, every location stands on equal footing. Your significance comes not from occupying a central position, but from your capacity to perceive, to wonder, to understand qualities that would be remarkable regardless of where in the cosmos they appeared. The beauty of a centerless universe also manifests in what it allows to emerge, because space expands uniformly, with the same physical laws operating everywhere. Complex structures can form throughout the cosmos. Stars ignite, planets coalesce, chemistry evolves toward biology, consciousness emerges. These processes aren't confined to special central regions, but can occur anywhere conditions permit. The universe's lack of center creates a kind of open canvas where complexity can develop in countless locations. This distributed creativity represents another form of cosmic elegance. Rather than concentrating complexity and significance at a central point, the universe allows for their emergence throughout its vast expanse. Life and consciousness aren't special because they appear at a privileged location. They're special because they represent remarkable developments that could, in principle, occur anywhere with suitable conditions. The universe doesn't need to place consciousness at its center because consciousness isn't about position, it's about perception, regardless of where it occurs. The absence of a cosmic center also allows for a certain freedom of motion. In a universe with a true center, there would be a preferred reference frame, a standard, against which all motion could be measured absolutely. But without a center, motion becomes purely relative. There is no absolute rest, no privileged perspective from which everything else moves. Each observer experiences their own frame of reference, equally valid to all others. This relativity of motion, formalized in Einstein's theories, represents another aspect of cosmic democracy, the equality of all reference frames, with none able to claim absolute status. This freedom extends beyond motion to encompass orientation. In a centerless universe, there is no absolute up or down, no cosmic vertical axis. The directions we use, up, down, north, south, east, west, are convenient local references, not cosmic absolutes. An observer on the opposite side of Earth has a different up than you do. An observer in a distant galaxy has a different north. Yet all these perspectives are equally valid, equally aligned with reality. The universe accommodates this multiplicity of orientations because it doesn't impose a central reference point or preferred direction. As you drift closer to sleep, imagine how this centerless structure enables your very existence. The elements in your body, the carbon, oxygen, nitrogen, and other atoms that form your tissues, were forged in ancient stars through nuclear fusion. When those stars exploded as supernovae, they scattered these elements through space, where they eventually became part of the molecular cloud that formed our solar system. This process of element creation and dispersal happens throughout the universe, not just in some special central region. Stars form, live, and die in galaxies across the cosmos, each contributing to the enrichment of space with heavy elements. The materials that make up your body could have been created anywhere. Conditions permitted stellar formation and evolution. Your very substance represents atoms that were born in stellar furnaces, scattered through the centerless expanse of space, and eventually incorporated into a planet that developed the conditions for life. In this sense, you are quite literally a child of the cosmos, not of a central cosmic region. but of the universal processes that operate throughout space according to the same physical principles. Your atoms have experienced the entire 13.8 billion year history of the universe. They were present at the Big Bang in the form of energy and elementary particles. They witnessed the formation of the first atoms, the coalescence of the first stars and galaxies, the birth and death of ancient suns. Now they form your body and brain, participating in the remarkable phenomenon of consciousness. This cosmic heritage doesn't require you to be centrally positioned. It connects you to the universe, not through special placement, but through shared composition and history. You are made of the same stuff as the stars, governed by the same physical laws that operate throughout the cosmos, participating in the same grand evolutionary process that unfolds across the universe according to consistent principles. As the night deepens and sleep approaches, rest in the beautiful symmetry of a universe without a middle. The cosmos doesn't revolve around you or any other point. It expands uniformly, carrying galaxies along with it, creating space and time at equal rates throughout its vast expanse. In this centerless arena, life emerged on at least one planet. Consciousness developed. Beings evolved who could contemplate their own place in the cosmic structure and recognize the profound symmetry of a universe that expands everywhere at once, with no preferred center. You float now, not in the center but in the flow. The cosmos moves gently, expanding in all directions, carrying galaxies along its currents. And you are already part of its rhythmo-conscious participant in the grand cosmic dance, significant not because of where you stand, but because you can contemplate the dance itself. Not because you occupy a central position, but because you perceive the beauty of a universe that has no center and needs none. In this centerless cosmos, you drift toward dreams. The stars wheel overhead, the galaxies recede in the distance, and space stretches silently in all directions. There is no center to find, no special place to seek. There is only the vast, expanding fabric of the universe, and your consciousness flickering within it, like a star unique, not because of where it shines, but because it shines at all. Tomorrow, in our final chapter, we'll explore how the centerless nature of the universe might relate to potential multiverse scenarios, and what this means for our understanding of cosmic origin and structure. But for now, rest in the beautiful symmetry of a universe that doesn't choose favorites, doesn't establish hierarchies of position, doesn't crown any location as special. A universe that treats all regions with perfect equality, allowing complexity and consciousness to emerge wherever conditions permit. Significant, not because of central placement, but because of their very existence in the vast, centerless, cosmic sea. As consciousness ebbs and sleep draws near, carry with you this final thought. The beauty of a universe without a middle lies not in what it takes away the illusion of central importance, but in what it offers. The freedom to find significance beyond position, the invitation to value consciousness wherever it appears, the perspective that connects rather than centralizes. In this centerless cosmos, you are neither elevated nor diminished by your location. You simply are where you area thinking, feeling participant in the grand unfolding of a universe that expands with perfect symmetry in all directions, asking only that you witness its beauty from wherever you happen to be. Throughout our journey, exploring why the universe has no center, we've examined scientific evidence, philosophical implications, and the beauty of cosmic symmetry. In this final chapter, before our conclusion, let's step back and consider how the narrative of cosmic evolution unfolds in a centerless framework, how the universe's story takes shape when it has no privileged location from which everything began. Traditional creation myths across cultures often begin with action at a specific place here, cosmic mountain, a primordial ocean, a divine workshop. These stories reflect our intuitive understanding of beginnings. Events start somewhere specific and radiate outward, but the universe's actual story, as revealed by modern cosmology, follows a different pattern known where the beginning happened everywhere at once, and where the subsequent chapters unfold uniformly throughout all of space. This distributed narrative challenges our storytelling instincts. We're accustomed to tales with central characters, primary locations, and focal points for action. But the cosmic story has no main stage, no single arena where the primary drama unfolds. It's a story that happens everywhere simultaneously, with each region experiencing the same fundamental processes while developing its own unique variations and details. The opening chapter of this universal story, what we call the Big Bang, wasn't centered at a particular location. It wasn't an explosion in pre-existing space, but the beginning of space itself everywhere at once. The initial conditions, incredibly high temperature, density, and energy, existed throughout all of nascent space. The same fundamental processes occurred in every region: the formation of elementary particles, the slight predominance of matter over antimatter, the emergence of the fundamental forces of nature. As this story continued, space expanded and cooled uniformly. About 380 years after the beginning, temperatures dropped enough for electrons to combine with protons, forming neutral hydrogen atoms and allowing light to travel freely through space for the first time. This moment, what astronomers call recombination, happened throughout the universe simultaneously. The cosmic microwave background radiation that we detect today represents the light released in this universe-wide transition, coming to us from all directions because it occurred everywhere at once. The next major chapter, the formation of the first stars, began roughly 100 million years after the Big Bang. In the darkness of the early universe, hydrogen and helium gas began to clump together through gravitational attraction. When these clumps reached sufficient density and temperature, nuclear fusion ignited, and the first stars blazed to life. This process didn't happen at a special central location. It occurred throughout space wherever conditions allowed gas to collapse into stars. These first stars were giants, perhaps hundreds of times more massive than our sun, and burned hot and bright but died quickly in spectacular explosions. Their brief lives and violent deaths served a crucial purpose in the cosmic narrative. They forged heavier elements in their cores and scattered them through space when they exploded. Carbon, oxygen, silicon, iron, the elements essential for planets and life, were created in these stellar furnaces and distributed throughout the cosmos. This enrichment of space with heavy elements didn't radiate from a central point, but happened throughout the universe as the first generation of stars lived and died. The cosmic story unfolded in parallel across the vastness of space, with each region experiencing the same fundamental processes of stellar birth, evolution, and death. The formation of galaxies, the next major chapter, followed a similar pattern. The slightly denser regions in the early universe grew progressively denser as gravity drew matter toward them. These density contrasts, visible as tiny temperature fluctuations in the cosmic microwave background, were distributed randomly throughout space. There was no special central region where galaxies formed first or most abundantly. The cosmic web of galaxy clusters, filaments, and voids emerged throughout the universe as gravity acted on these initial random fluctuations. Within these galaxies, generation after generation of stars formed from gas clouds enriched with the heavy elements from previous stellar deaths. About 4.6 billion years ago, in an ordinary spiral arm of an ordinary galaxy we call the Milky Way, one such cloud collapsed to form our Sun and its planets. This event wasn't central to the cosmic narrative, except from our perspective. Throughout the universe, similar processes were creating countless other solar systems with their own unique characteristics. On at least one of these planets, the one we call Earth, conditions allowed for the emergence of complex chemistry, then biology, then consciousness. This remarkable development doesn't require Earth to be at the center of anything. The processes that led to life and intelligence could, in principle, have occurred anywhere with suitable conditions. The cosmic story doesn't privilege any location for the emergence of complexity. It creates the conditions for complexity to arise wherever circumstances permit. This distributed narrative, this story without a main stage, has profound implications for how we understand cosmic purpose and meaning. Traditional creation myths often identified a central purpose for the universe: to serve as a home for humanity, to manifest divine will, to play out a predetermined cosmic drama. But a universe without a center suggests a different kind of purpose, one that doesn't focus on a special location or privileged species, but encompasses the vast variety of phenomena that emerge throughout cosmic evolution. In this view, the purpose of the universe, if we can speak of purpose at all, might be simply to exist and evolve according to consistent principles, allowing complexity to emerge in countless forms wherever conditions permit. The cosmic narrative isn't directed toward a single goal or concentrated at a central location. It's a distributed story of evolution and emergence playing out across billions of galaxies over billions of years. This doesn't mean the universe lacks meaning or significance, but it suggests that meaning isn't imposed from a central point or concentrated in a special region. It emerges throughout the cosmos in the form of structure, complexity, and consciousness. The universe doesn't need a center to have meaning, just as a symphony doesn't need a single loudest note or a forest doesn't need a central tree. Meaning arises from patterns, relationships, and developments throughout the whole. Consider how this centerless narrative affects our understanding of time in cosmic history. With no spatial center, there's also no temporal center, no special moment that could be considered the middle or focal point of cosmic evolution. The universe's story unfolds continuously, with each era flowing into the next without privileging any particular epoch as the most important or central. We might be tempted to view the present moment as special as the temporal center of cosmic history, but this is just another form of the observer bias that once led us to place Earth at the center of the universe. From our limited perspective, the present naturally seems central because it's where we exist and observe, but the universe doesn't assign special status to this or any other moment. Each era plays its role in the ongoing cosmic narrative. This temporal democracy parallels the spatial democracy we've explored throughout our journey. Just as no location is at the center of cosmic space, no moment is at the center of cosmic time. The universe's story has a beginning, the Big Bang, but no middle, no focal point around which all other moments revolve. Each instant simply is what it is, own moment, in an ongoing evolution that treats all epochs with the same fundamental principles. The centerless narrative also changes how we think about cosmic significance. In stories with central characters and locations, importance tends to concentrate around these focal points. The hero is more significant than secondary characters. Events at the main setting matter more than peripheral happenings. But in a universe without a center, significance cannot be determined by proximity to a special location or central event. Instead, significance emerges through complexity, consciousness, and connection. A region of space isn't important because of where it's located, but because of what happens there, the structures that form, the processes that unfold, the awareness that develops. Earth isn't significant because it occupies a special position. It's significant because it's where, as far as we know, matter evolved to the point of becoming conscious of itself and the cosmos that produced it. This shift from central positioning to distributed emergence as the source of significance offers a more democratic and inclusive cosmic perspective. It suggests that meaning and importance can develop anywhere conditions permit, not just in privileged central regions. It opens the possibility that consciousness, complexity, and meaning have emerged or could emerge in countless locations throughout the vast universe. Each instance significant not because of where it occurs, but because of what it represents: the universe's capacity to evolve systems capable of perceiving and understanding themselves. As sleep approaches and your thoughts grow more diffuse, consider how this centerless narrative changes the way we understand our own place in the cosmic story. You are not a character at the center of the universe's plot. Neither you nor your species, nor your planet, nor your galaxy occupies the main stage of cosmic evolution. And yet, you are fully and completely part of this grand narrative, a participant in a story that unfolds throughout the universe, according to the same fundamental principles everywhere. Your atoms have been part of this story from the beginning. They were present at the Big Bang in the form of energy and elementary particles. They experienced the formation of the first atoms, the emergence of structure, the birth and death of ancient stars. Now they form your body and brain, participating in the remarkable phenomenon of consciousness, the universe's capacity to perceive and comprehend itself. This cosmic heritage doesn't require you to be centrally positioned. It connects you to the universe, not through special placement, but through shared composition and history. You are made of the same stuff as the stars, governed by the same physical laws that operate throughout the cosmos, participating in the same grand evolutionary process that unfolds across space and time. In this sense, you are a character in the universe's distributed narrative, not the main character around whom everything revolves, but an equal participant in a story that has no center, no periphery, only the vast unfolding of matter and energy according to consistent principles throughout space. Your significance comes not from where you're located in this story, but from your capacity to comprehend the story itself, to recognize your connection to the cosmic whole and your place in its ongoing evolution. The centerless narrative also changes how we think about the future of the cosmic story. With no privileged location or focal point, the universe's evolution continues throughout space according to the same fundamental processes. The accelerating expansion, driven by dark energy, will eventually isolate galaxies from one another. Stars will burn out. Black holes will evaporate through Hawking radiation. Entropy will increase toward a state of maximum disorder. But these processes don't converge on a central location or privileged region. They unfold throughout the cosmos, treating all regions with the same physical laws. The universe's future, like its past and present, plays out across all of space without favoring any particular location. This distributed future invites us to consider cosmic significance in terms that transcend locality and centrality. If meaning emerges through complexity, consciousness, and connection, then the future of meaning in the universe depends not on what happens at a special central location, but on how these phenomena evolve throughout the cosmos. Will consciousness continue to develop and spread? Will intelligence find ways to preserve complexity against the increasing entropy of the universe? Will awareness survive in forms we cannot yet imagine? These questions concern not a particular place, but the capacity of the universe as a whole to maintain and evolve the remarkable phenomena that have emerged within it. The cosmic story has no center, but it does have characters, conscious beings like ourselves who participate in and perceive its unfolding. The significance of these characters lies not in their location, but in their awareness, their ability to comprehend and perhaps influence the next chapters of the universal narrative. As your consciousness ebbs toward the shores of sleep, rest in this centerless perspective on the cosmic story. You float not at the focal point of universal history, but within its vast unfolding. You are neither the main character nor a mere extra, neither at center stage nor in the wings. You are simply one conscious participant in a grand narrative that plays out across billions of galaxies over billions of years, with no special central region where the primary action occurs. In this distributed story, your significance comes not from where you are, but from what you perceive, from your capacity to understand the very centerlessness of the cosmic narrative and your connection to its ongoing evolution. You matter not because you occupy a special position in the story, but because you can comprehend the story itself, because you represent one instance of the universe's remarkable capacity to evolve consciousness, to perceive and reflect upon its own existence. The universe's story without a center invites a certain cosmic humility. You are not the protagonist of universal history, not the focal point around which cosmic evolution revolves, but it also invites a cosmic dignity in a narrative that unfolds everywhere at once, with the same fundamental processes operating throughout space. Your consciousness represents a remarkable developmental capacity for awareness and understanding that would be significant, regardless of where in the cosmos it emerged. As sleep draws nearer and thoughts grow more distant, carry this perspective with you. You are part of a cosmic story that has no center, a narrative that unfolds throughout the universe according to consistent principles, creating the conditions for complexity and consciousness to emerge wherever circumstances permit. Your significance in this story comes not from central positioning, but from perception itself, from the remarkable fact that through you, the universe has developed the capacity to perceive and comprehend its own existence. Tomorrow, in our brief conclusion, we'll gather the threads of our journey, the scientific evidence, philosophical implications, and aesthetic dimensions of a universe without a center. But for now, rest in the peaceful awareness that you float within a cosmic narrative that encompasses all of space and time, treating every region with the same fundamental principles, creating the potential for meaning and significance, not through central placement, but through the emergence of consciousness itself, the universe's capacity to witness and understand its own grand, centerless unfolding. The stars do not orbit a throne, the galaxies do not spiral from a hub, the universe does not grow from a dot drawn in the dark. It expands without edge, without anchor, and in doing so, it frees us from needing to be central. You are not at the center of everything, but you are not far from it either, because in a universe without a middle, every place matters. Every direction leads somewhere. Every point participates equally in the cosmic expansion. Throughout our journey, we've explored the scientific evidence, showing that the universe has no center, from the uniform recession of galaxies to the symmetry of the cosmic microwave background radiation. We've seen how computer simulations confirm that observers anywhere would experience the same pattern of expansion. We've considered the philosophical implications of this centerless cosmos and contemplated its profound beauty. We've discovered that significance doesn't require centrality, meaning doesn't depend on special placement. In a universe that expands uniformly in all directions, with no preferred center, our importance comes not from where we are, but from our capacity to wonder, to understand, to connect. The universe hasn't placed you at its center, but it has produced in you the remarkable ability to comprehend this very fact, to grasp the vastness and symmetry of a cosmos that expands everywhere at once, with no preferred hub. And in that consciousness, that capacity for understanding, lies a significance that transcends any geometric centrality, any special cosmic address. Sleep now, not in the center but in the flow. The cosmos moves gently, expanding in all directions, carrying galaxies along its currents, and you are already part of its rhythmo-conscious participant in the grand cosmic dance, significant not because of where you stand, but because you can contemplate the dance itself.